whether it works?
Sure.
Can you share the screen? Cor, jij bent nog gemute. You're still muted. Morning, Manuel.
Yep. Okay.
Yeah,
Now it's on. Ja, geluid is aan. Share screen. Hoe ging dat ook alweer?
First, Jerry is going to... So Jerry, please go ahead, if you can. Cor, jij bent nog gemute.
Will, we are now online in the YouTube channel.
Morning, Manuel.
Good morning. Just morning.
Yep. Okay.
So people, it's best if people mute if they are not speaking. Yeah, so that's better because sometimes we get an echo.
Ja.
Jerry, are you trying to present?
Yes, I am trying.
Yep.
Yes.
Can you see that?
Yes.
Yes, we can see.
And maybe now full screen. Yeah. Yes, it works.
Good. Don't
Okay.
see any problems now.
No, okay. So maybe you can unpresent now, then we can have some of the other speakers stop sharing. Cor, can you have a go?
Who do you want to present now?
Yeah. Who?
Cor is going to
Oh.
try.
Okay, I will try to present full screen.
Good morning, Maria.
Oh. He doesn't want to.
Hello.
Good morning.
I didn't see the previous presentation appearing. I only saw myself. I don't know sure yet. I'm looking for the answer. So now
Okay,
he's
we will test you. So now Cor is going to.
okay.
Try to present. Yeah.
Yeah, and it says Cor Hurkans
Yes.
dance, but I see myself. So I
You
don't
see
know.
yourself. Okay. What about you? I have now full screen.
I can see Cor's presentation well.
Yeah, we see Cor.
What is it then?
Okay. Shall I go back then?
Yes, please. Yeah, so it works for you.
It works for me now. Try to figure out how to
Yeah.
not present.
Yeah, there is a button. Stop sharing somewhere.
Yeah, somewhere.
Yeah.
Okay. Yeah, well, it's hidden by my
The
stop sharing is. I'm now presenting. Stop sharing.
yeah, very good.
Okay.
Hans, would you like to have a go?
I will try to connect again. I'm not sure why.
Okay, good.
Maria, if you are using Google Chrome, on the bottom right.
No, she's not. She's not online at the moment, Manuel.
Sorry.
Can you see my screen?
Yes.
Automatically solving and designing Sudoku and other constraint puzzles.
No, we only see the directory now.
Yeah, the directory we see, the Sudoku PPT and or Adobe.
Something is.
So Maria, now you see what was presented.
Maybe you're sharing the wrong screen. The easy thing is to take full screen.
Yeah, but okay, this is only. Yeah, but I should allow something.
No, yeah.
Let's see. I can try to do it again.
Hmm.
Is there something visible?
Directory only.
Oh, that is not what I see. I see my screen.
Yeah, but we don't.
Okay, so then
You probably selected to share this with me.
I stop presentation and try again.
Yeah.
Een venster, I can choose full screen. Yes.
Yes, yes. Choose full screen.
And then I should say allow.
Yeah.
Select window or screen.
Yeah. Now you go to your presentation.
Yeah, no, but I cannot. I cannot allow. Entire screen.
Entire screen. Yeah.
Allow doesn't work. I have to click on allow and it doesn't work.
Yeah, but you have to click on the middle screen maybe first, and then it will turn blue, I think.
Now something was allowed.
Yeah.
Yeah.
Yes, this looks promising.
Yes. Yeah. Okay. Control L and then you're done.
And now it's full good. And now you can see it?
Yes. Yes.
Yes.
Okay.
You see it.
Maria, do you see it?
Yes, I see it now. It's okay.
Good. So,
Okay.
present,
So
please.
I'll go back and now I do present off.
This is infinite. Now I see an infinite number of screens, but
Scherm delen stoppen. Yeah.
Yeah.
Okay.
Maria,
Should I
please.
try? Okay.
Yes, try.
Full screen. Entire screen. Allow. And now I go to my presentation.
Oh yes, looks promising. Very good.
Okay.
Yeah.
Yes.
Okay. Then I go back and stop here. Okay. Great.
Okay. So now I should try as the last one. Let's see. Present now. Full screen. Can you see the presentation?
Sudoku fun, but also serious mathematics.
Yeah. Okay. So
Yeah.
that works as well. Okay, good. And I stopped sharing, did I? Yes.
Your name is unknown.
Yeah.
Maybe that's not
Okay.
intended.
Sorry?
Will, your name is unknown.
Oh,
All other
that's
people
good.
have a name, but your name is unknown.
Aha. Okay.
Onbekend in Dutch. So
Yeah. Mm-hmm. Strange. Let's see.
well, maybe it's no problem if we can show your slides, then it's okay. But it's a
Yeah,
little bit
that-
strange that
yeah, but,
all of us have names and you don't.
Yeah, very strange. No, I don't see. Manuel, do you know how this works?
Yeah, I think that you don't have a Google account assigned to this session, so
Oh,
I think that's why.
ah,
Okay.
yeah,
So
I'm not. I don't
I
have a
think
Google account.
both of us should have a Gmail or something, and you just have the cookies, so we know the name, our name. Okay, that's the name on
Yeah,
our Google
okay.
account. I think so, but I'm not sure. But I think it's the main problem.
Yeah.
I think if you just open your
Okay.
Gmail, then it will know who you are.
Yeah, Cora, I think you are right.
Yeah. Okay, Danesh, are you online? Danesh?
Hello.
Hello, Danesh.
Yeah, I'm online, sir. Yes.
Okay, good. Please give us instructions.
Sir, could you? I would like to talk on your your WhatsApp phone. Can I talk to you for a minute? Yes.
Yes, I can. Yes, I will. Yeah. So we will start in about 2 minutes from now.
Will, the last 5 minutes of each presentation are for questions, yes?
Yeah, so speakers have 25 minutes, except myself.
Yeah, okay.
And then there will be 5 minutes for questions.
Okay,
But it's also possible if the questions come in during the talk and are urgent in a sense to explain something, then we can interrupt, the chairman can interrupt and ask the question.
Okay, thanks a lot.
Yeah. The first message is coming in. So Manuel, do you know, they said that messages also from questions from YouTube can also come in, but how do they come in? I mean, how do they reach us?
At the moment, I have 2 screens, and I am checking the YouTube channel, so I can check questions over there. I think they are not redirected to the Google Meet, but I'm not pretty sure. But I don't think so.
Oh, very good, very good. Thank you very much. So Danesh, are you still online? Okay, so what should we do? I mean, shall we start soon or? Let's just wait 1 or 2 minutes to see what's happening. So Manuel, what do you see on the YouTube channel? The same as we see, or?
It has a delay of about 1 minute or something. So
I see.
in 1 minute, you can see yourself talking in YouTube.
Hello.
Yes.
Hello, Will. Will. Vice Chancellor sir will join later after some minutes. So maybe
Okay.
we start in that way. But he will join.
Okay,
Okay.
good. Then please inform us when he's available, and we can start.
Yes,
the
exactly.
session. Yeah.
Yes, yes. So he will join, but yes.
Yeah. Okay, so welcome
Just a
everybody.
minute.
Sorry?
Yeah, it's okay. Go ahead, sir. Go ahead. Yeah.
Okay. So welcome everybody to this webinar, which was kindly organized by the University of Baroda. In the last few weeks, we had several webinars, one on mathematics for industry, and 2 weeks ago about mathematics and COVID-19. And they were all very interesting and also very successful with many participants. And so this also gave us the idea of organizing a webinar on Sudoku and mathematics. Sudoku is fun. It's played by many people, young and old. But it's also mathematically very interesting. There are many people that use Sudokus as examples for their methodologies.
Will, hello.
Yes.
Sorry to disturb you.
Yes.
I mean, before that, I mean, somebody would like to speak about our Vice Chancellor. So then you can start. Yes.
Okay, good, good. Then please go ahead.
Yeah, yeah. Yes, start.
Namaskar and a warm welcome to the webinar on Sudoku, Fun and Serious Mathematics, jointly organized by Office of International Affairs and TU Eindhoven, the Netherlands, in collaboration with Department of Applied Mathematics, Faculty of Technology and Engineering, and Department of Mathematics, Faculty of Science, the Maharaja Sayajirao University of Baroda. I'm given an extremely delightful task of introducing an extremely versatile and dynamic person, our Honorable Vice Chancellor, Professor Parimal Vyas. Professor Vyas has been serving the Maharaja Sayajirao University of Baroda continuously for the second term as Vice Chancellor for from 11th February 2019. And prior to that, he has also served as an acting Vice Chancellor and Pro Vice Chancellor for the university from December 2014 to February 2016. He has been He has been a Vice Chancellor from February 2016 to February 2019. He has the distinction of being the very first dual or joint professor of Faculty of Management Studies and possesses more than 15 years of teaching, research and administrative experience as professor of the University of Baroda. Under his able leadership, the university has achieved reaccreditation of National Assessment and Accreditation (NAC) with A grade with 3.16 CGPA in 2016. Besides this, the university has been placed in World Times Higher Education Ranking (THE) from 2016 to 2018 and also in QS ranking in the year 2018. The university has been adjudged as the best university and also has been awarded three national and international awards. Professor Vyas, a distinguished academician as an able academic administrator, has also been nominated several times as the chairman of NAC peer team, chairman in several committees constituted by the University Grants Commission, New Delhi. He has also been an active member with various national and international boards and state boards. Professor Vyas as an acclaimed professor of management, has been honored with 11 awards of best research paper with publication and has authored various books. To his inspiring personality, he has always been motivating and passes the same to all his peers. He has a unmatched personality, and matching his enthusiasm is a task for youngsters with his working pace and ability. It is worthy to note and applaud that in his second term, he is having the same enthusiasm and dynamic personality. And during this pandemic situation, he has been constantly helping teachers develop their skills. He has been a staunch advocate of e-governance and initiatives, and under his guidance, various collaborative webinars and expert talks with highly knowledgeable speakers and motivators have been conducted. He is always positive for all the initiatives and startups for all the staff members. With this note, I would like to invite our Vice Chancellor, Professor Parimal Vyas, who will be joining us soon in the later half of this webinar.
Okay, thank you very much for the introduction. So Professor Vyas is going to join us later in the session. Okay, Danesh, please instruct us.
Yes, sir, you go ahead. You go ahead, sir.
Okay. I think it's time to give the floor to Manuel Cruz, who is the first chairman for the first session. Please go ahead, Manuel.
Thank you very much, Will. My name is Manuel Cruz, and I'm greeting you from Portugal with a really nice 25 degrees sunny weather. Good morning to all the entities from the America time zones. Good afternoon to those from Asia, and good evening to the ones who are in Australia, New Zealand, and so on, timelines. I have the great honor to introduce our first speaker, Professor Wil Schilders. Wil Schilders worked at Philips Research for 30 years and is with the Eindhoven University of Technology since 1999. He's very much interested in connecting academic mathematics with industrial challenge, and as such, is an active member in several European organizations like the ACME and EU Maxim. In 2004, he got interested in Sudoku, and this has only grown over the years. He wrote a number of books on how to solve Sudoku, with the basic book being translated, I think, in 8 different languages. But besides fun, he also recognized that there is a lot of serious mathematics behind Sudoku. So he will now give a brief introductory presentation entitled Sudoku, Fun but Also Serious Mathematics, an Introduction. So thank you very much, Professor Wil, and you may start your presentation.
Okay, thank you very much, Manuel, for the nice introduction. And can you see my screen?
Yes, yes, Wil, we can see your screen.
Okay, then thank you very much. So what I will do is give a very short presentation to introduce people to the subject, and then the speakers of today will go into much more detail. So let's start at the beginning. The rules of Sudoku are clear, I hope. But just to refresh, we have a 9 by 9 diagram with which is also subdivided into squares of 3 by 3, and every row, every column, and every smaller square must contain the numbers 1 to 9 precisely once. So that's simple rules. And the other thing is that the solution of a puzzle should be provably unique. So multiple solutions are not allowed. This would not be nice if you solve a puzzle which has 5 different solutions. So I mean, Sudokus are supposed to be unique, have unique solutions. Hans Santema, who is the first speaker today, he knows a lot about how to construct Sudoku puzzles. And he also wrote a book on this. It's in Dutch, the Achterkant van Sudoku. But so this goes into detail on how to construct Sudokus, not on how to solve Sudokus. Now, how to solve Sudokus? I mean, usually you can start with some simple logical steps. And if you look at this example, you look at the 5th column, and then you see that there are 3 numbers missing, 1, 2, and 6. But the number 1 cannot be in the middle square because there is already a 1 in the middle square. So the 2 positions in the middle, in the 5th column, they are not applicable. So the 1 has to go into this. Can you see my mouse?
Yes.
Yeah, so it must go in that cell. Yeah, so, but then you can also make the conclusion that the 6 and the 2 go here. So these are simple logical steps to solve a Sudoku. And this Sudoku can be solved with such steps without too many problems. Now, there are other procedures to solve a Sudoku. Some people advocate the use of writing down all the possibilities in a cell. So you take a certain cell and then you see which numbers can be here. Clearly, there cannot be a 7 and a 5 here. And you can eliminate more options, the 4, the 6, and the 2 in this column. So then you write down the 4 remaining options for this cell, and you do that for all the cells. It's a lot of work, apparently, and also often no strategies are provided on how to proceed with this information. Furthermore, it is not very much fun because it looks like a human working like a computer. Yeah, so would not recommend this procedure. What I do usually is advocate the use of number pairs. So what you see here is a puzzle that has been partly solved. The numbers in the white cells, they were given. The ones in the gray cells, I already filled in. And then on the way, I denoted number pairs when I know that, for example, in this cell, we can only have a 1 and a 5. So I denote 1, 5 in the top left corner of the cell. But then you see that there are also some number pairs that can correspond to each other. For example, this cell can only contain a 4 and a 6. This cell can only contain a 4 and a 6. But then the conclusion must be that these 2 cells contain 4 and 6 in some order. And 4 and 6 cannot be in these remaining cells anymore. Same holds for 5, 8, 9, and 5, 8, these 3 cells. And you see that these 3 number pairs tell us that the 3 numbers 5, 8, and 9 are in these 3 cells. But that means that this number here, there was an option of 1 and a 5 in this cell left over, but then we can forget about the 5 in this cell. And so then we know that this cell should contain the digit 1. Yeah, so using number pairs, you can make also conclusions about numbers to be filled in, digits to be filled in. Now, there are more complicated procedures. One of them is called the X-wing, and I think Jerry will also have an example. This is a puzzle that has been solved up to a certain point, but then we got stuck. But then we make the observation that there is a so-called X-wing in the puzzle, and it works this way. We look at the 3rd and the 9th row, and we observe that the number 8 can only go into these gray cells. Now, if we suppose we would put an 8 in this cell here, in the 3rd row, 1st column, then that implies a 5 over here in 9-1, and the 5 then implies an 8 in this cell here. Vice versa, if we start with, if the 8 in this row would be here, not here, but here, then this implies a 7 down here and an 8 here. So if we summarize this conclusion, if the 8 is here, then the other 8 is here. And if the 8 is in 3-8, then the other 8 in the 9th row is over here. Yeah, so they form a cross or an X-wing. But this means that the 8 is always either in one of these two and in one of these two. And so in all the other cells in between, so the non-gray cells, we can eliminate the option 8. And there is a cell here with options 2 and 8. We can forget about the 8, so we know that there is a 2 here. So the pattern of an X-wing can be used to eliminate numbers and to find new digits in the Sudoku. There are more of these patterns. I mean, people have identified a lot of different patterns, and they are also given very strange names sometimes. For example, this is an extension of the X-wing, now with 3 rows and 3 columns, and it's called the swordfish. And in this case, that leads to the elimination of the 2 in 6-8. And so there can be a number 8 here, is the conclusion. There are also some other patterns, Y-wing, W-wing, jellyfish, exocat, etc., like the rocket. So they all have very nice names, and but they are often difficult to detect. So Jerry, for example, he wrote a book on solving Sudoku. And in this book, he discusses quite a lot of these patterns and solution strategies. What I usually do is different. I mean, so if we are stuck after some logical steps, then usually what I do is I start guessing in an intelligent way. Yeah, so what we could do is we could take a cell where there's only 2 numbers possible. For example, this cell here. We know that there is a 2 and a 6 possible. And we can explore both paths. So what happens if we fill in a 2 here? And what happens if we fill a 6? And we can do that at the same time, so parallel processing. So that's why I denoted these numbers in gray. And all the numbers that result from the choice 2 will be denoted in gray on the left side of a square, and with the choice 6 on the right-hand side. I hope that's clear. And now we proceed filling in more numbers in the diagram with these 2 choices. And this is a result. Yeah, so the 6, for example, leads to a 3 in this cell. We don't know what the number 2 leads to in this cell, so I just write an X here, but the 2, for example, leads to a 6 here. So you can do a few steps for both choices, and this is the end result. And what you now observe is something very nice. You see that in some cells, there are double digits. So both the 2 and the 6 lead to a 4 in this cell, a 9 here, and a 4 here. So what we can do is we were denoting these numbers by pencil. We can erase all these numbers and fill in the Manuel, am I still presenting?
Somebody start presenting over you, but we can see now your presentation, but only on your screen.
Yeah.
I am not with the administrative rights, so I cannot do anything about it. Okay.
But do you still see my presentation, or?
Yes, I see it in your screen. Yes, yes.
But is it smaller now, or?
Yes, yes, it's smaller. Yes.
But somebody else is taking the screen, or?
Somebody did it, but can you try to?
I stopped sharing
again. Yes.
The abbreviations are in Dutch, but GP stands for number pair. You start with number pair. You explore the 2 paths for the 2 options, and maybe you will have to use another number pair again with 2 options, and then this can lead to good or wrong answers, and there will only be one that will be correct path. So, but sometimes it can be several levels deep. Yeah, so for example, and I discussed this in my books that Manuel already mentioned. They have been translated in a number of languages. So here you see also the websites associated with these translations. For example, you need these techniques for the world's most difficult Sudoku, which was designed in 2012 by Arto Inkala, Finnish mathematician. You can have a go at this one, but I promise you that it will be a lot of work. No digit can be found with logical steps, so immediately you're stuck. So you will have to do the intelligent guessing. And in this case, there's only one number pair in the puzzle, which is in 8-7, which is this cell, and that's the pair 3-9. So you can use that as a starting point and then start solving the puzzle. Yeah, and Sudoku turns out to be 5 levels deep, so sit down for an afternoon and you will be able to solve it. There are even more difficult ones. 2019, another step was made, and one of the speakers today, Veit Elzer from Cornell University, he made this Sudoku, and he's using that also for his mathematical methods. This puzzle does not even have any number pairs. It only has triplets. But we can still use the intelligent guessing procedure. We can start with a triplet. Turns out that every triplet leads to number pairs in the puzzle. So then you can start, well, the highest level is 3 options. But if you then descend, you will always have 2 options. So the number of paths is 3 times 2 times 2 and maybe 5 times a 2. Yeah, so this is very, so take 1 or 2 days to solve this one by hand. Okay, so that was a brief introduction to the fun part of Sudoku, but there's also serious mathematics for Sudoku. From a mathematical point of view, you can associate many questions with Sudoku. For example, how many numbers do we need? I said in the beginning that we need that the solution should be unique. Well, how many numbers, how many digits do I have to provide to ensure that it is unique? Another question could be which patterns of prescribed numbers will lead to correct Sudokus. Japanese Sudoku designers usually make them by hand, and they know patterns that will lead to unique solutions. Another question is total number of distinct Sudokus. I will come back to that. Or is there always one number pair in a uniquely solvable Sudoku? And we know already that the answer is no. But the Sudoku that I just showed by Veit is one of the very few exceptions. Usually there is at least one number pair in the Sudoku. And the question is also a case of the last resort method, what is the meaning of the double digits? So 2 paths coming together at some point. Yeah, so why does this happen? Okay, starting with the first question, minimum number of clues is 17. That's the answer, and I will not go into detail. Gary Maguire from University College Dublin in Ireland, he solved this in 2012. Yeah, so there was a conjecture that 16 clue puzzles with unique solutions do not exist. And he used actually an enormous amount of CPU time, 7 million CPU hours, at the Irish Centre for High-End Computing in Dublin to go through all these 16-digit grids and analyze the situation and prove that indeed 17 is the minimum number. Laura Thalman, who wrote a book on taking Sudoku seriously, so with a lot of mathematics in it about Sudoku. It's a very nice book, together with Jason Rosenhaus. And well, it's obvious that she says that, I mean, the approach taken is will take some time for others to get enough computing time to check the proof of Gary Maguire, which is clear, of course. I mean, 7 million hours of computing time is not what you want to spend. But there's also a nice book on if people are interested in mathematics of Sudoku. Number of distinct Sudokus, that's an enormous...
Sorry, you have 2 more minutes, yes? Okay.
Yeah. Number of distinct Sudokus, 6 times 10 to the 21, so that's a dazzling number. Distinct means that at least one number in the puzzle is different, so we don't count symmetry relations, etc. It was originally, this number was given by Günther Stertenbrink in 2003. But in 2005, Bertram Felgenhauer, he actually proved it using group theory methods. And this is the other formulation of the number. Felgenhauer, I also invited him for this seminar, but he had no time. But he won the Mathematical Olympiad silver and gold medals in 1905 and 96, for example. But so there's a big number of distinct solutions. In a similar direction, when I was traveling in 2012, I got called by a Dutch newspaper who had come across the paper on the right, and they thought that maybe this would be a method that could be used by humans. I don't think so, but Maria can tell us more about this. She will be a speaker today, and it's also, again, a very nice paper that she wrote in 2012. Then finally, graph coloring problems and Sudoku. We'll not go into detail. You can read it later if you like. But so Sudoku is also related to the graph coloring problem. The graph coloring problem is MP complete. And so enable to get solutions or approximate solutions, you need approximate methods. One of them is the KMS method that has been suggested in 1998. And today, Veit will talk about this. He has been using the Douglas-Rachford splitting algorithm, which is originally a numerical method published already in 1956. But Veit suggested to use this algorithm to iteratively find solutions to semi-definite programming tasks. And Francisco Aragon, Ruben Campoy, and Veit proposed several alternative versions of this method and use these to address Sudoku problems. And he will talk about that later today. Furthermore, there are other ways of solving Sudokus from the area of mixed integer programming, and Cor Herkens is a speaker who will tell us more about this today. So that brings me to the conclusion, Manuel. Sudoku is not only fun, but also a subject of quite a few very interesting mathematical works. There are some basic questions, but there are also some advanced questions. And we were also interested in deterministic ways of solving Sudoku. They have been developed, for example, by relating Sudoku to graph coloring problems or Boolean satisfiability. And if you're interested, I mean, just type the words Sudoku and mathematics in Google, and you will find many more interesting mathematical works on Sudoku. Thank you very much.
Thank you, Professor Will, and thank you very much for your very interesting presentation. I would like to warn the attendees that they can place questions on the Google Meet forum and also on the YouTube channel. Although in the YouTube channel, the questions come with 1 or 2 minutes of delay. So. Okay. This is just a warning for the next presentations also. I have 2 small questions that are in order to get us in schedule. Given your vast experience while solving and teaching how to solve Sudokus, do you think that a mathematical background helps to solve it in a more efficient way?
Thank you very much, Manuel. Well, yes, I mean, so you can debate about this, but I think, I mean, the way mathematicians think is in a structured way, usually, and trying to see structures in puzzles, etc. So I think it helps. It's not necessary, of course. I mean, you can also solve Sudokus if you don't have a mathematical background, but I think it can help, yes. I mean, yeah.
Okay, okay, thank you very much. And just another final and small question is that you solve, I think, the most difficult Sudoku that you present a few slides earlier. Yeah. And did you solve it only using the Sudoku sheet and the pencil, or do you need something more?
No, I only solved it. Yeah, so it takes time. Yeah, so the one from 2012 I can do in a half a day, and indeed, well, it takes perseverance, but you can do it. I mean, if you just but you have to start, well, in that case, you can only start with one number pair, but then after that you have different number pairs, and it takes some experience to select the right number pairs for the intelligent guessing procedure. But I mean, yes, but I only do it with a pencil and eraser, yes.
And you don't need it to Xerox to copy the original Sudoku.
No.
With only one sheet of paper.
Yeah.
Okay. Thank you very much, Professor, and thank you for your wonderful presentation. And let's now proceed to the next phase. Okay. Thank you very much.
Okay, then I will take over from you, Manuel. Thank you very much. And I should say that Manuel and I together are responsible for the Portuguese version of the Sudoku book. So, yeah, so I would like to introduce the next speaker. It's Hans Zantema. He's a colleague from the university in Eindhoven University of Technology. He's a professor of computer science. He got his MSc from the University of Groningen, that's far north in the Netherlands, in 1979. And his PhD from the University of Amsterdam in 1983. He worked at the company Philips as well for a number of years. Then he went to Utrecht University, and since 2000 he's in Eindhoven. His main field concerns applications of term rewriting and theorem proving, but he has also a big interest in Sudoku, as I already mentioned in my presentation. You can see his webpage for a lot of details. And today he will tell us how to automatically construct Sudoku puzzles. So Hans, the floor is yours.
Okay, thank you. And now I try to get the screen. Entire screen. Can you see it?
Yes, it's working.
Okay, so I want to say something about automatically solving and designing Sudoku and also other constraint puzzles. Okay, my background, Bill already told it. I'm a mathematician and currently I'm employed at 2 universities in the Netherlands. And I designed many Sudokus and other constraint puzzles. You can find it on my webpage, and this is the page particularly on Sudoku puzzles and variants. And the book I wrote on Sudoku was already mentioned by Will in his presentation. Okay, I first consider the same Sudoku as Will considered, just a partly filled 9x9 diagrams, and then we have to solve it. And where Will mainly focused on doing this manually, we will focus on how can we do this automatically? How can we do this with the use of a computer? Well, roughly we can say there are 2 possible approaches. The first one is we program it directly, and then we use backtracking. And the other approach is we express the requirements of the defining requirements of the puzzle in a formula and solve this by some external tool. And I will mainly use SAT SMT solvers, but the mixed integer programming, as Cor Hurkens will present, is also an example of this. Okay, both of them I will say a little bit more about it. Well, what's the idea of backtracking? You try to solve a Sudoku, and the idea is very simply exactly the same as what you do as a human. As long as the Sudoku has not yet been solved, that means it still contains an empty cell. We have to do something. We try to fill the empty cells. And what do? We choose an empty cell. And for all numbers 1 to 9, we check whether it is allowed on the empty cell. And if so, we continue for all cases. And here, the most simple definition of allowed is that we simply say that the number is not in the same row, column, or square block. And if we only do this without any optimization, then typically it is not efficient at all. This computation may blow up exponentially. Let's say typically if you choose an arbitrary empty cell, maybe there are 5 values allowed. Then for the first choice, we have 5 choices, and for the second one also 5, but there are many empty cells, and then we get 5 times 5 times 5 times 5, and this is a very big number. So if we do not do any optimization, this is unfeasible. But it's always correct by construction, and we can easily improve efficiency. And improving efficiency can be done that we say we do not choose just an empty cell. No, for every empty cell, we check how many allowed values there are. And if we start with one with few allowed values, then the procedure becomes much more efficient. And we can fine-tune the notion of allowed. We have seen the ideas of number pairs and X-wings and things like that. And by that, we can fine-tune this notion of allowed. And we can add forced moves. For instance, if there is, we can fill in a number that is allowed in only one position in a cell of a row, column, or square block. And if we do that, well, we do not miss any power of the procedure, but we can increase the efficiency. And many other approaches. And in this way, the computer programs roughly follow the same scheme as how a Sudoku is solved by a human. And in a simple computer program, you have only very simple procedure, and you can improve this whenever you like. Okay, that's the main idea as doing it by backtracking. And roughly we can say we do the same as a human, but there is a main difference. The advantage of the human is, as a human, you have some intuition where you say, well, that is a good position, let's try this one. And the computer does not have intuition, so then you typically choose the first one and so on. So that's definitely the advantage of a human. But the advantage of a computer is definitely, if we have to do a few hundred steps or a few thousand steps, for a computer, that's no problem at all, and that's done in a fraction of a second. While for a human, for instance, Will Schilders, who is doing the most difficult Sudoku by hand, it will take a day or half a day. So simply following simple steps in that, doing that hundreds or thousands of them is very easily done for a computer, and that's for a human much harder. But for the rest, we can say the approach is of a backtracking program by a human and by a computer program has quite some similarities.
Sorry, Hans, to interrupt. There are some people who are not muted. Can you please mute your microphones?
Yes, I think this already helps.
One guy, I see that you're not muted. Can you please mute? Thank you. Okay, go ahead, Hans.
Okay, this was about the backtracking human, so without external tools. And next, I want to say something by not programming everything yourself, but simply use an external tool. Instead of programming backtracking yourself and optimizing, making the choices, you can also use standard tools. And then the idea is we simply express a formula in some language, and then the language for which you have a tool, and then simply give the definition of the rules of Sudoku and no more than that. And then we have built this formula, and then the external tool will try to find the solution of this formula. And one format of that is SAT SMT. SAT means satisfiability, and that is just a Boolean formula with conjunctions and disjunction and negations and no more than that. And satisfiability just means, can we find a value in such a way, values on the Boolean variables in such a way that the formula yields true? That is satisfiability. And we can also already express Sudoku in pure satisfiability. An extension is called SMT, Satisfiability Modulo Theories. And Z3 is a strong and freely available tool for that. And then you can also deal with, let's say, linear inequalities. So this is what I already said about satisfiability, and SMT is the same for richer formulas, typically dealing with numbers and linear inequalities. And one fruitful feature in SMT is that we have an operator distinct. Distinct is just an operator on which you can, that has as arguments a number of variables, and then the requirements is that these variables should be distinct, as the name already suggests. And now we can easily express all Sudoku requirements in an SMT formula. What do we do? For all 81 positions on the field, we declare an integer variable. So we have aij for I and j running from 1 to 9. And what are the requirements? So the goal of the puzzle is just we have to find values for these a's, all being from 1 to 9, with some restrictions. What are the restrictions? Well, they have to be values from 1 to 9. So that is the first requirement. Every aij should be greater or equal than 1 and less or equal than 9. And in every row, the values should be distinct. So here we express it for row I. This expresses that the values in row I are distinct, and exactly the same we do it for every column and for every square 3 by 3 block. We just enumerate the 9 variables that should be distinct according to the definition. We could also describe that not only distinct, but every number should occur, but that's redundant, since if we have values from 1 to 9, and that should all be distinct, that's completely equivalent as saying that every number occurs exactly 1. And finally, of course, we have the given values in the Sudoku. If on position ij the value k is given in the Sudoku, we just add the requirement aij is k, and that is what we do for every given value. And now we have a formula, and now on this formula we can apply an SMT solver, and typically it gives the solution, the full solution of the Sudoku, within a fraction of a second. Okay, that is about solving Sudoku, and now I want to go into designing a Sudoku. Maybe you don't realize, but every Sudoku in a newspaper or in a puzzle book or in an app has been designed in one way or another.
Sorry, Hans, somebody else is presenting now. So the person presenting, can you please go away? Janavi Bisht, please stop presenting. Can you please stop presenting? Can one of the moderators of the session get her to stop? Yes. Okay. Thank you, Hans. Yeah, I
Can
think.
I continue?
Yes, I think but you have to share your screen again.
Oh, my screen is not shared anymore. Then
No.
I will try to do it again. Let's see.
This is the disadvantage of online meetings. I mean, in a real meeting, you would not have somebody write on your blackboard, yes? But
and now something should happen. Is it visible again?
yes, and now you can make it full screen.
Yes.
Okay, good. Thank you.
Okay. Well, sorry. Well, let's continue.
Yeah.
Okay. Every Sudoku that you find has been designed in one way or another. And typically it's not made public how it is done, but of course it has been done somewhere. And now I will present some ways on how you can do that. Well, in designing a Sudoku, if you solve it, you can ignore the fact that it has a unique solution. But in designing a Sudoku, you should be aware that a crucial property, which is often left implicit, is that it has a unique solution. This was already mentioned in the presentation of Wil Schilders. That's part of the game. A Sudoku with no solution is not of interest, and more than one solution is also not of interest. It should have exactly one unique solution, and that is what we are trying to find. So the question is how to design such a Sudoku with a unique solution. Well, it turns out that once you have a program that can solve a Sudoku quickly, and no matter whether this is based on backtracking or using an external tool, typically a minor modification of it can be used to design new Sudoku puzzles. So this may be either a standalone program doing backtracking or a tool calling an external tool. Both work well. And what's the modified program? We are now not trying to solve a solution. No, we have not only Sudoku, a partially filled Sudoku, but we also have one solution of this Sudoku. So we have a Sudoku for which we already have a solution. And now the question is, does it allow another solution than the given one? And you can imagine if you do this by hands, you can say, well, simply ignore the given solution and try to solve it. And if we only do 4 steps and we find the given solution and no other one, we know then indeed the answer is no, there is no other solution than this one. And if we can find another one, if we have the extra given property that we are looking for a solution different from the given one, well, maybe then we could find it. And both in the backtracking program and in the approach where you use an external tool, you can easily modify the program in such a way that it finds an answer on this question. So the input is not only a Sudoku, but also a solution of the Sudoku. And once we have this modified program, we can say start by any solution of any Sudoku, and then, well, let's say remove one cell, and then clearly it still has a unique solution. So if we would apply this modified program, the answer is there is no other solution. But now we remove one by one more fields. So we repeat calling the modified program, and as long as the answer is no, so there is no other solution than the known solution, then we remove one more cell and then apply the modified program yourself again. And then it's clearly, if we would have removed all cells, then, well, then the answer would be yes. So somewhere in this procedure, we will find a Sudoku for which the answer is yes, and one step before, and the answer is no. And if we do not take the one where the answer is yes, since then it does not have a unique solution, but we take the one before, this may be an interesting Sudoku puzzle. And this is the main idea, or a main idea, in this way of designing new Sudokus. So that's a basic way to generate Sudoku puzzles. And we can do many variations of this idea. I said remove an arbitrary cell, but we can remove not an arbitrary cell, but a particular one, and we can follow particular patterns and things like that. And often you may have a nice pattern in mind. For instance, this one, the given values are only on these nice diagonals. Or the example I showed on the first slide, also having a nice pattern. If you have a nice pattern in mind and you want a Sudoku with this nice pattern, you can say, well, what can we do? We simply start with the Sudoku solution and we remove all cells outside the pattern and then check whether it has a unique solution. That means, does it have a solution different from the given one? If it's the case, well, then it's not a Sudoku, but then simply start again by another Sudoku solution until you find one for which the solution is unique. And then you may be happy. You can say you have a new Sudoku with this nice pattern. And it depends on the pattern. If you have a pattern with only a few given numbers, it will be very hard to get it. So the pattern should satisfy some requirements, but then this works well. Okay, so far about solving Sudokus, normal Sudokus. Now I want to go to variants of Sudokus. Since the same idea, both in the backtracking and in the use of external tools, we can also add some more requirements, and then we can not only solve and generate Sudokus, but also variants of Sudokus. And now I will show a number of variants. A first idea, and that is what you also often see in books or puzzle books. There are many puzzles, Sudoku puzzles, where we have the extra requirement of the diagonals. So apart from every row, every column, and every square block has the values from 1 to 9, all being distinct, it also holds for both diagonals. But we can add more requirements. We can say we do not take the usual 3 by 3 blocks, but we can make other shapes. And if we make other shapes, we are not restricted to 9 by 9. So here we have an example. We see we have some fat blocks, and here it's 7 by 7. And in the fat blocks, we can say, well, this fat block should contain the number, all numbers from 1 to 7, all occurring 1, and also this one, and also this one. Every fat block has 7 cells, and these cells should contain the numbers from 1 to 7, all occurring ones. And the same for this diagonal and that diagonal. And then again, this has a unique solution, and the puzzle is to find the solution. Okay, so this is one variant. We can take many more variants. For instance, we can draw a circle. That means that the corresponding values are consecutive. And we can draw a cross line, meaning that they are not consecutive. And then we can have a puzzle like this. So here we see the 3 and the 4 who are neighbors, and indeed the 3 and 4 are consecutive. So there is a circle in between. Here the 1 and the 4 are not consecutive, and there is a cross line in between. And now the question is, we have to solve this puzzle. So the extra requirements is that everywhere we see a circle, the corresponding number should be consecutive, and if we see a cross line, they should not be consecutive. And we also see many borders on which there is neither a circle and neither a cross line. Well, then both are allowed. So here there is nothing between the 5 and the 4, but well, we could say it could have been a circle, since we know 5 and 4 are consecutive. And then again, this is a variant of Sudoku, and that you can solve it by similar techniques as I presented. But it's also a nice puzzle for doing by hand. Next puzzle is Futoshiki. You can also, if you Google it, you find online procedures, and you find apps for your smartphone. Again, in every row and every column, all numbers should occur exactly once. And this requirement is called a Latin square. But in Futoshiki, we have no fat blocks. But we have an extra feature, namely the greater than symbol, and that just means greater than. And then we can have a puzzle like this one. This is a puzzle for values, again, 7 by 7. And every box, a number from 1 to 7 has to be filled in such a way that every row and every column exactly contains the numbers 1 to 7, all occurring once. For some cells, the value is already given. And for some others, it's given that this value should be greater than 2, and this value should be greater than this value, and so on. And now you have to fill in the whole puzzle. And this is also a nice type of puzzle, and quite similar to the Sudoku, but well, it's a nice puzzle to do. The next one is Killer Sudoku. And in Killer Sudoku, you have extra blocks of which the sum is given. So here is this is how a Killer Sudoku looks like. And again, we have to fill it in just like a normal Sudoku. Here we have 3 by 3 square blocks. But every small extra block what is given, for instance, this one where we see 17, then we know that these 3 values in this block should sum up to 17, and they should be distinct. Well, that's a Killer Sudoku, and Killer Sudoku is also a nice puzzle to do. A final one I want to mention is the link puzzle. It was invented by me. It's not very well known for the rest, but it's nice to mention. It has a completely other feature. Again, in every row and every column, all numbers should occur exactly once. So it's a Latin square. But there is one more requirement. Once we have a Latin square, as in this solution, we can make a graph, and we make a graph by saying in the Latin square, all neighbors, so both straight or diagonal, if the difference of the values is at most 1, we connect them, and if the difference is greater than 1, we do not connect them. And in that way, we get a graph. And now the requirement is that this graph should be connected. And if you take an arbitrary Latin square, then in many cases, the graph is not connected at all, and then it's not allowed as a solution. So as a solution, we only allow a connected Latin square according to this definition. And then a puzzle could look like as is given here. So not all connections are given. So some connections are given and some numbers are given, but not all numbers and not all connections. And now you have to fill in the whole Latin square in such a way that the result is a connected thing. And this is a completely new feature. And also the way you solve such a puzzle is quite different. You have non-local requirements, and this notion of connectedness is completely different as what you normally have in Sudoku. Also for programming it, it's harder. I did it by SMT solving, but even then you cannot directly describe connectedness of a graph. You have to find a good characterization of connectedness of a graph, but you can do that and you can express it in SMT. And then by the approach I explained here, you can solve and design this kind of puzzles. Okay, so two main approaches to solve a Sudoku by a computer are: we can encode backtracking ourselves, we can follow the same, and where roughly we follow same principles as in human solving, or we can express the constraints and we apply an external tool to solve them. And then designing a Sudoku can be done by repeating, applying a slightly modified program. And that's not only for Sudoku, but also for several related puzzles. I mentioned a few of them. And all puzzles I showed were generated by myself in the approach I explained here, and many of them can be found on this webpage. Thank you.
Okay, thank you very much, Hans, for this very interesting presentation. And indeed, I would advise people to have a look at your website. There's a lot of information there. There's also some questions that came in. To start with the last one that refers to the puzzle where you had the circles and the bars, yeah. I think, so consecutive. There was a question, can consecutive be generalized using some fixed difference? For example, stating that the difference should be 2 or something like that between the numbers.
Yeah, you could also do that. You can find many variants of this, and if you say you have a fixed difference, that's also easy to express. And you can directly express this in, well, I think both in an external tool, SMT solving, but you could also do this by backtracking. And you simply introduce a notation for that, and you have a new type of puzzle. That's true.
Yeah, okay. Another question was, can machine learning or deep learning help in solving Sudoku problems?
Sorry, can you repeat the question? It was some problem with the noise.
Yeah.
With the sound.
Okay. Yeah, can machine learning or deep learning help in solving Sudoku problems?
I think so. The main approach I want an exact solution. But if you have a hard puzzle and you have to do a good guess, essentially what you did by what you called in your presentation intelligent guessing, I think learning approaches and things like genetic algorithms and neural network and things like that could really help for that. But it's important to realize if you want to design a computer, a Sudoku, you should be aware that you should be sure whether there is a solution or not. And all of these techniques can only help for finding a solution. But if it does not find a solution, you are not sure that no solution exists. So this if and only if requirement you typically do not have in these learning approaches. And if you want to design a Sudoku, you need it. But indeed, for cleverly solving a Sudoku, it may help. It may help, yes.
Okay. Then, I mean, you're constructing Sudokus, but how can you get a certain level of difficulty in designing these Sudokus?
Yeah, that is indeed quite, well, a first point is how do you define difficulty? And that can even be personal. So it's very hard to give, to find an objective measure of what do you mean by difficulty. And even two persons can disagree on which Sudoku is more difficult than others if they have different techniques. Then the one may say this one is easy and the other one is hard, and other people say it's the other way around. That may happen. So it's very hard to find it. But roughly you can say if you have a lot of choice, then typically the puzzle may be harder. Yeah. And if there are steps you can do with only, well, in your terminology, if you have lots of number pairs, it's an easier Sudoku than if you have only a few of them. So you can give measures of that. And it's not always easy. In designing puzzles, then typically you have the approach to do it, and then you can check how difficult it is. So essentially what I did when I wrote my book, I generated zillions of Sudoku puzzles and simply applied programs on that, measuring the difficulty, and I ordered them according to the difficulty. So it's quite hard to say in advance, I want a Sudoku puzzle of this particular difficulty level, and then I press a button and I have it. That's not how it works. You say you have a machinery to develop Sudokus, and you have a way to measure it. And then if you want one with a particular difficulty level, well, simply generate enough until you have the one with the desired difficulty level. That is the way how I did it. But maybe other people have other approaches. That is just what.
Yeah, maybe Maria will go. I mean, I know that in her paper she has some way of assessing the difficulty of a Sudoku.
Yes. Okay.
Final question maybe for you, Hans. Maybe difficult, but what is a real-life application of Sudoku? I mean, are there any real-life, or is it only for fun?
Well, I think I think having fun is a main application. So I think that's yeah. So I think being happy and having fun is a main goal in your life, and I think that's sufficient as an application. And I think if you do this kind of things, you do not have another application in mind than only that. But you can say you get a lot of insight how combinatorial problems behave and how programming behaves. And that gives a lot of insight in both combinatorics and programming. So that's also of interest. And that could be applied on other approaches too.
Yeah, yeah.
And SAT-SMT solving has many applications in many areas, and playing around with Sudoku-like puzzles gets a feeling of what you can do by these techniques, and that may help for getting other applications. So from that point of view, there are relationships with other applications.
Yeah.
But the main thing is just having fun and being happy.
Yeah, okay, and it's good for the brain as well, I think.
Yes,
huh?
yes,
So,
for sure.
Yeah. Okay, Hans, thanks very much. Well, we don't have a way to applaud, but thank you very much for your presentation.
And now I will try to stop my presentation.
Yeah.
Okay.
And then we turn to the next speaker, which is Maria Ercei Ravaș from Romania. She is a professor of physics at the Babeș-Bolyai University and the Transylvanian Institute of Neuroscience in Cluj-Napoca in Romania. Maria, maybe you
Yes.
can still mute a little bit.
Yes, hello. Hello, I'm here.
Can you mute your microphone for a moment still?
No, it's unmuted. You don't hear me?
Yes, I do hear you, but I mean, I would like to ask you to mute for a moment.
Oh, sorry.
Yeah, thank you. It was an echo. So after obtaining the PhD in physics and information technology, she spent 3 years as a postdoctoral researcher at the University of Notre Dame in the USA, and she returned to Romania with an ESC starting research grant, also obtained the Marie Curie Fellowship. In 2012, she wrote a very nice paper that I showed already in my presentation about the chaos in Sudoku, and she's now going to tell us more about this. So Maria, the floor is yours.
Thank you for your invitation. Now let me try to share it. Full screen. Okay, you see me? I mean, you see the presentation?
Yes.
So we started this research together with Professor Toroszkai when I was a postdoc at the University of...
Sorry, Maria. So somebody else came in between. Can you share again?
Sorry.
No, it's not your problem. I mean, somebody else was presenting.
Yes, okay. Okay.
Yes, and now slideshow.
Is it okay now?
Yes, it's okay. Thank you very much.
Okay, thank you. So we started this research when I was a postdoc at Notre Dame with Professor Toroszkai. And the truth is, at the beginning, we didn't even think about solving Sudoku. So our first goal was to solve constraint satisfaction problems with analog dynamics. Also, during my PhD, as I worked with analog computing systems, and as physicists, we were interested in these type of problems. And first, we designed coupled ordinary differential equations to solve the Boolean satisfiability problems. And we discovered interesting things with the SAT problem. And only after that came the idea to transform Sudoku into SAT form. And then we observed that the hardness of problems appears as transient chaotic behavior in the dynamics. And that's when we define this new kind of hardness measure, which can be applied on individual problems. It gives a more, as Professor discussed previously, that it's hard to say about usually a problem, how hard a problem is. But this is a hardness measure. It's more objective. We called it the Richter scale of Sudoku. So I will start now at the Boolean satisfiability problem. Now, of course, this slide was made for physicists. I don't have to mention for you the importance of the SAT problem. What is important for me here is that for our algorithm to be implemented, we need the SAT to be in conjunctive normal form. So I have the n Boolean variables, the m clauses. When these constraints are all inside the constraints, we have only the OR operation, and the literals are the normal or negated forms of the Boolean variables. So for example, this is a 3-SAT clause. So after having this in this form, so our question was, how can we program physics? Now, what do I mean by this program physics? Imagine you have the problem like Sudoku or a SAT problem, and can you design a continuous time nonlinear dynamical system? That would be our algorithm, which has the attractors and equilibrium states that would be equivalent to the solution. Because if you design such a system, then you can start that system from any initial state, and it will find the equilibrium state that would be the solution of the mathematical problem. So that was the starting idea. And we did this for the K-sub problem. And we transformed it into a continuous, using continuous variables, we transformed it into a global optimization problem, such that the global minimum of the energy were the SOT solutions. I will show you more exactly how we did this. And we defined a deterministic system of ordinary differential equations with certain desired properties that finds the global minimum. So the attractors are always equivalent with the solutions, and it never gets stuck in local minima. So here there were two interesting observations: that in the hard SOT phase, transiently chaotic behavior appeared, and the other was that we were able to achieve a polynomial scaling of the analog time if we allowed unbounded fluctuations in the energy. So because we have a continuous dynamical system, not a discrete, not a digital computer, we were able somehow to trade time with energy. Of course, the cost remains exponential. You need the extra energy, but you gain time if you use extra energy. And how did we transform K-SOT? Here it is. We introduce continuous variables between the interval of between -1 and 1. So -1 is corresponds to the false, 0 and the 1 is the true. And this CMI matrix describes the structure of the SOT problem. So if the variable I is not present in the constraint M, then it's 0. If it's present in normal form, then it's +1. It's in negated form, then it's -1. And then for each constraint or each clause, we can write up a cost function in this form. And you can notice that if a literal is missing from the constraint, then the corresponding term is just 1. But if its a literal is true in that constraint, then the corresponding term is 0, so the whole product is 0, and the constraint is satisfied, meaning the cost function is 0. So this cost function, and of course it's normalized, so the cost function is between 0 and 1, and 0 meaning that the constraint is satisfied. So it gives us an energy function in this form, where the 0 energy would mean that we have found the SOT solution. Now, of course, there are many local minima, and that is where comes the hard part. So how to define a dynamics that can escape these local minima and find a global solution. And for this reason, we introduced auxiliary variables. So we modified this energy, this function, this cost function, as a weighted sum. So each clause has its own auxiliary variable. And variables, the S variables, they follow this gradient descent along the energy landscape. But the auxiliary variables are allowed to increase when the constraint is not satisfied. Notice here, in this differential equation, if the constraint is satisfied, meaning this k is 0, then the auxiliary variable doesn't grow, it just stagnates. But when it's not satisfied, it is allowed to grow even exponentially. So it can jump from time to time when it's needed exponentially fast. And this is a key point in the dynamics. Only this way it can escape efficiently from these local minima. During the dynamics, these auxiliary variables somehow allow to change the landscape of the energy function in a way that the dynamics doesn't get trapped in a local minima, but always converges after a time to a solution. And first we presented this in a Nature Physics paper in 2011. We have shown that this has important properties, like the dynamics always stays in this hypercube, so we cannot get out of the -1,1 interval, and the solutions are stable fixed points with macroscopic attractor basins, and there are no limit cycles. So, and the dynamics can never get trapped in local minima. And as I mentioned already, there were these two interesting observations that hardness somehow is related to chaos, and energy can be traded with time. So you can gain time with energy in a physical system. And here I just show you a few examples, and after that I get to Sudoku. But just to show you how in an easy sort problem the dynamics of these variables evolves, it fastly converges to the solution. In a harder sort problem, it searches a much longer time and more chaotically. It's called transient chaos in this hard sort phase. When you have a solution, so it will converge to an attractor, but still before that it's you have transient chaos. And in unsought it searches until infinity. And this is again interesting. Here I show the auxiliary variables. So you can see that most of them stagnate most of the time, but a few of them have large and fast jumps from time to time. And this is what helps the dynamics to escape the local minima. And also this one allows this energy function to have these large variations. And that helps the dynamics to be efficient. So here I show you a movie for first just on a very small problem to be able to follow all the four variables. So we have only 4 variables and 6 clauses, and here I plot the dynamics of the black dots has shown the dynamics of the starting from the middle of the hypercube, and the colors have shown the energy in a given plane. And as you have seen, sorry, yes, so it has found a solution. Actually, each solution cluster is one single attractor in our system. So here, for example, it finds 3 solutions practically at the same time. So it goes into an attractor that is built out of 3 solutions. Or here on a more complicated problem, this is much larger. So above you see how the V energy function fluctuates, and here I have 50 variables. So imagine it would be a 50-dimensional hypercube in which this dynamics moves on and searches. So it's very complex dynamics, and also I have the 210 auxiliary variables. Those makes, or some of them jump from time to time, increase. And here I always take a S1, S2 plane and S3, S4 plane out of that hypercube, and I colored it according to the energy function to show you how, or to get a feeling about how this dynamics can work, and it will soon find a solution. And we will see that in the solution, actually, yes, now it found it S1. So the first variable must be true, the second variable can be true or false, and the third variable true, fourth variable false. So it's these attractor basins give us the solutions. Sorry. Now let's get to Sudoku. So after we studied a lot this sort problem and the properties of the chaos and all the phase transitions and everything, but then came the idea that let's have some fun and turn Sudoku into sort form and try our algorithm on Sudoku. And how we, well, Professor Zantana already presented you most of it, how it can be turned into a sort form. Here we turn it in Boolean satisfiability, and it was important to finally get it into a conjunctive normal form. So imagine that I have this grid, and for each little square, I I allow 9 Boolean variables in a way that, for example, here if I have 4, then the 4th variable will be 1 and all other must be 0. Here I have 6, then the 6th variable will be 1 and all others must be 0. So in total I have 9 times 9 times 9 Boolean variables, but of course the given clues eliminate a lot of the variables. So there won't be, so many of them will be known already because of the given clues, because of the Sudoku problem. For example, if I look at the layer 4 in this cube, and where you can see that there are 3 4s given in this Sudoku, eliminate a lot of Boolean variables, so I don't have to deal with those. And after that, using the rules of the Sudoku, I can write up all the constraints. So I must write up that in the vertical columns, 1 and only 1 must be true. In the rows and columns and subgrids, and in each layer 1 and only 1 must be true. So usually it's a type of +1 in 9 sort formula, they call it. Actually not always 9, because many times the constraints are shorter, but that can also, again, can be easily transformed into conjunctive normal form. And the number of variables and constraints depends on the clues. In example, there were 22 clues and we got 232 variables. And here I show again the dynamics.
Maria,
yes?
Can I just the question on so 22 clues, but how do you get to the number of variables?
So how do I get to the number of variables?
Yes.
So in each layer, I get all the clues. So for example, in layer 4, I had 3 of these 4s, okay? And I eliminate according to the Sudoku rule. So if this is 1, because this is 4, then in this row, you cannot have another 4 digits. So all other Boolean variables must be 0. So I can eliminate that. You cannot give an analytical approach, but you can computationally easily do it for every Sudoku. So it's very complicated to say. So it's not an analytical form for that. How many variables will you have? Because it depends on how the clues are positioned, how many are there, and so on. But you can go over these layers, take all the clues and eliminate everything they practically fix. And then just work with the unknown variables, because it will be much more efficient.
Okay.
And here is an example how the dynamics works for an easy problem. First, I zoomed into this little square here, the subgrid, and in each little square, I show the dynamics of the 9 Boolean variables. Some of them you see they are fixed, so practically they are not unknown. Those are the ones which were shaded with gray. Yes, and here it's an easy problem, very fast it converges, and here you will get 9, 4, and so on. Here it's an easy problem because we have many clues, and the number of variables, what you get after transforming it into SAT form, it's only 126, and the constraint density after transforming it into conjunctive normal form, it's only 5.69. And of course, the length of the clauses varies in this. It's not like 3 SAT or 4 SAT, but can vary. But still, the constraint density is important here too. And a hard SAT problem, this search is much more longer, much more chaotic. The number of unknown variables is twice as much. The constraint density is much, much larger, 8.11, and so on. So this already shows you why this is much harder. Now, I also show you a movie here. So here, because I have this plus 1 in 9 type sat formulas, which say that one and only one in a little square can be true, you can see that always one of the curves dominates there. So one of the digits is in the square. That's how the dynamics also works. Like people try it out that only one digit is written in the square. So when I show you here the dynamics, I have plotted these numbers with colors and in the whole Sudoku puzzle. And again, in this little square, I show you all the curves of the Boolean variables, and you can see the chaotic behavior of the dynamics. But after a time, it just settles down and converges to an attractor and finds the solution. Now, as I said, because always one digit dominates in a little square, so one can also study how, until now I started from a random initial condition, but let's say I want to study these so-called attractor basins, how sensitive it is to the initial conditions. We did also that. For example, taking one little square, I plot as function of time which digit dominates at that moment in that little square. And in an easy problem, we fix a random initial condition and we change only the first two variables. I just wrote here S1 and S2, but it doesn't really matter. You just change two variables along a grid and color one point according to what digit is dominating in that little square at time 10 or 15 or 12, 20. And in easy problems, you see these nice smooth attractor Bayesian boundaries, but in hard problems already you get very complicated pictures with fractal Bayesian boundaries. Actually, we have shown already in the Nature Physics paper with Boolean satisfiability that we had fractal Bayesian boundaries. So it's important that because Sudoku always has a solution, this chaotic behavior is a so-called transient chaos. Professor Tamás Tél from Hungary has a nice physics reports paper about transient chaos, and he helped also us. Helped us. He gave us advices of what to look at it. An important property is the escape rate. So imagine I start the dynamics from many random initial conditions, and I plot the probability that it did not find the solution yet. So it starts from 1 in time 0, and it starts decreasing. It finds more and more of the dynamics of the started initial conditions, find the solutions. And when it's an easy problem, then most of them find it very fast. When it's a very hard problem, then this escape rate is very small, and it will rarely find the solution until a given time. So you have to wait more and more and more. Actually, we tried out a lot of problems. This was in 2012. So if you said that Professor Elser designed an even harder in 2019, I will have to try that out. But at that time, the hardest problems we have found were those that indicated by Wikipedia as the hardest ones. And by what do I mean by hardest? We define this hardness measure as function of the escape rate. And yes, sorry, I wasn't clear enough here. So it's important property of transient chaos that the end of these curves usually can be fitted as an exponential. They're not perfect. At the beginning it's not, but at the end is usually converges to an exponential decrease. And that exponential decrease, this kappa, is called the escape rate. So how fast does it escape that transient behavior and turns to the attractor? And this somehow tells you in a general way the hardness of a problem. So not only it doesn't depend on from where did you start, because you do a large statistics, so you start from many different initial conditions, and it gives you one measure about each individual problem, about the hardness of individual problems, and putting on the log scale this escape rate as function of the number of clues, you get this. And we said that these are the easy ones where the minus log of the escape rate is below 1. These are the medium, hard, and extremely hard ones. It's interesting that there are problems where the number of clues is very small, but it's still not extremely hard. So there is a correlation, but it's not that trivial. And as I said, the hardest ones were those that we have found on Wikipedia at that time in 2012. Yes, so I think this is it, the conclusions. So we used continuous time dynamical systems to solve hard constraint satisfaction problems. And related to Sudoku, we defined this hardness measure based on the transient chaotic behavior. We use the escape rate to define this measure. And I have to mention that this is not necessarily the only dynamical system. Recently, for example, we improved it to solve Maxat problems that are even harder. The idea or the initiative in this project as physicists for us was was related to analog computing, as I said, not necessarily to develop some very efficient algorithm to solve Sudoku, but more to study its properties and to design dynamical systems that are able to solve mathematical problems. And now, for example, Dr. Toretskoy is working with engineers, and they are trying electrical circuit implementations for solving SOT. So if one would be able to implement these type of dynamical systems in real physical circuits or other implementations, then it could be extremely efficient, because as I said, you can gain extra time by inducing more energy, which is an interesting property. Okay, thank you very much. Any questions?
Yeah, thank you very much, Maria. Very nice talk and very nicely explained. So if people have questions, they can ask them, of course, via the chat. Maybe to start with, I mean, you have been able to solve all the Sudokus that you put in the program?
Sorry, again?
You were able to solve all Sudokus you had?
Yes, yes. Some of them took very long time, but you see that in this slide, let me play from here. So all of the curves, if I zoom in, all of the curves go below 1, meaning that that a few times I solved them. So, but I'm curious about that. You said that Professor Esser designed in 2019. I will look that up.
Yes. I mean, you can find it, and it would be interesting to see what your program does on that. Because that's another question. I mean, what is the highest number of the hardness level that you found so far?
So what is the hardest?
So if you go to your next slide, I think.
Yes. It's
so
it's around.
You found some extreme one. 3
so what
point
is the highest?
something or other.
Yes, 3 point,
Yeah.
I don't know, 3.5 around, if I remember correctly. There is, it's our paper is written what are the highest numbers, but we didn't find anything with this eta measure larger than 4, for example.
Yeah.
So these
Yeah.
were the errors. I mean, we didn't try more, but we did try quite a lot. So
Yeah,
I
it would
don't
be
know.
interesting to see. I mean, there are companies that produce Sudoku puzzle magazine, and they have a number of stars associated with the puzzle, from say 1 to 15. It would be interesting to see if that corresponds to your scale. Yeah, so if they have the hardest one, it's also one with an extreme, well, at a greater than 3, say.
Yeah, can you maybe send some links to that magazine? So because I don't know them so much.
Yeah, I can send you some Sudokus and we can check that. Yeah, but
Okay.
agrees.
Okay.
Would be interesting.
Okay.
Are there any
Thanks.
questions from the people in the audience?
Yes, I would like a question.
Yes.
Yes.
You built your formula by saying I do not have all 729, that's 9 to the power 3 variables, but you
Yes.
already pruned out a lot of them.
Yes.
You could also have started with just having all of these variables and simply then express in these that a given number, the corresponding variable is already true, and for the rest, you simply keep it in the formula. Then your formula is a little bit bigger, but it's more structured.
Yes, it's more structured, but you know what's the problem? We have a huge differential equation system that, I mean, really huge. And if you leave
Okay,
all
so
that extra,
then the differential equations become too large to deal with.
I mean, you can solve it in that way too, but it's really much more efficient. And when solving it on digital computers, it does matter, unfortunately.
Yeah, but if you're only interested in the measure of hardness,
Yes.
would this change the notion of hardness, or would it be the same?
No, I don't think so, because those variables were very quickly stuck
Removed.
in those
Yeah, okay.
those values.
Yeah,
So
indeed, that's what I expect, but
yes,
glad
that
to
would
hear that you also have the same thing.
directly convert to what I fixed, because it just fixes just those constraints would be satisfied immediately, and that would fix the values of those variables. So it would not change. I don't think
Okay.
it would change
Thank
at
you.
all.
Okay, Marie. In view of time, we have to stop here. So thank you very much for your talk.
Yes, thank you. Let me stop sharing.
Yes. And then we quickly go to our next speaker, which is Cor Hurkens. He's also from the university, the Department of Mathematics and Computer Science at Eindhoven University of Technology. His areas of expertise include operations research, software, algorithms, control systems. And Cor's research focuses on worst-case analysis of all kinds of combinatorial algorithms, complexity of all kinds of combinatorial problems, solution methods based on polyhedral theory, and approximation methods based on local search. Cor is also involved in applied mathematical modeling, supervising industrial projects, and writing papers on mathematical methods. He's an expert in problem solving and very hard to beat, as some colleagues tell me. But today he will speak about solving and designing Sudokus using mixed integer programming. Cor, floor is yours. Please unmute, Cor. We cannot hear you. We can see the presentation, but we cannot hear you, Cor.
Now I'm.
Yes,
You can hear me now?
Yes, but now we don't see your screen, the presentation.
Yeah, I had to.
Oh, I see. Now we see it.
Yeah, I had to move to the meeting to unmute myself.
Okay, good.
Okay, so I will tell about using mixed integer programming for solving and designing Sudokus. which fits nicely in the track set by Hans and Maria. Maria already mentioned the way to use this binary representation. I will come to that. So when we tackle Sudokus in arbitrary sense of size n, we have our partial filled matrix with rows and columns labeled 1 up to n, and also taking n cells, and a partition into blocks or regions, of which we have n of those, and each region has size n. And the symbols also come from 1 to n. And now we are asked whether there exists such a completion of our matrix such that row, column, and region each contain every symbol once. And a first question as a mathematician you may ask, is that really, what's a computational complexity? And but that's of course a rather theoretical question. It has been shown that solving the standard Sudoku for arbitrary n is NP hard, and it's only it has to do with completion of Latin squares. But the trick is hidden in the n. So only for a very large n and complex, bad choices of it, these things really become complex. For n is fixed, n is 9. It's actually a trivial problem because there's only a finite number of options. Well, okay. Actually, to find that solution is, of course, the concern. And you want to do that in a good way to find it if it exists. And once you have found it, you also want to be able to answer the question whether it's unique. And as inputs, I give here 2 examples. On the left-hand side, the standard block Sudoku. And on the right-hand side, it was also mentioned by Hans, the jigsaw Sudoku. But for the MIP formulation, these are actually indistinguishable. We simply have blocks, regions of size n, and the symbol, whether it's a square or something ragged, it doesn't make any sense, any difference. Right? So let's immediately turn to the mixed integer programming formulation, where we use indicator variables x. Those are binary variables with arguments row, column, and symbol, which take the value 1 only if at that position we will put that symbol. And if you go for a description with binary variables, okay, the first thing is to describe a vector in a space. So that's our x. It's a huge 0, 1 vector that we're looking for with n cubed variables we have. And then the formulation should consist of linear expressions, linear constraints, equations or inequalities, and also a linear objective. That's allowed in mixed integer programming. We see that we have 4 n squared equations, simply saying for every field we have to pick a symbol, for every row symbol combination we have to pick a column, for every column symbol combination you have to pick a row, and for every block symbol combination you have to pick 1 cell out of that block. And in addition, we say these variables should be in an interval, usually it's in between 0 and 1. And of course, for those positions where we have a prefixed value, actually the range is only 1. The variable x can only take the value 1 there. We take separate the condition that x has to be an integral variable. And we have kind of in the concept for Sudokus, this comes a bit extra, we have an objective. But that's nice because we will see that we can use it for different purposes. Okay, actually, okay, let's go into how do we solve MIPS. If you want to solve MIPS, actually, you would like to get rid of this integrality constraint. That makes life different. If you drop it, then what is left for you is a linear programming problem. This is called the linear programming relaxation. So you have the same description except for the integrality. And then we have a kind of simple thing that you have seen in linear algebra or in linear optimization or whatever bachelor you followed. And this can simply be solved using the simplex method or an interior point method. But of course, this is a continuous. This is x in Rn cubed. And for n is 9, okay. So here we talk about 729 variables for 324 equations, some boxing constraints, that's it. Okay, but the idea about mixed integer programming is simply, okay, solve the LP and hope that you're lucky. If you're lucky and the outcome is accidentally already integer, then you're done. And if you're not, okay, then there is some, or at least one position where the x variable is strictly between 0 and 1. And then, of course, then what we do is we distinguish subcases. Say on the one hand, we consider all solutions that have x on that particular argument equal to 1. And in the other subcase, we reserve all solutions where x takes the value 1. Take care that this is not an even split, right? So if you fix position 1, then you already fix a lot of possibilities for the remaining variables. Whereas if you fix a variable to 0, then you have still 728 other variables that can do what they want. That's not completely true, but in any solution we are looking for, we only have 81 variables that are supposed to take a value 1, and all the rest is 0 anyway. So fixing something to 0 does not do very much. And the bad thing about this is, of course, you still have to solve the subcases. And you really have to solve both subcases before you can know the answer of the main problem. And in order to solve the subcases, you might have to recursively create other subcases. So you will actually create a Benjamin Brown tree that might explode in your face. And to make life even worse, if you look at some LP solution that could come out of this LP relaxation, there can be many. So, okay, of these 729 variables, fortunately, almost all of them are 0. So these are the remaining non-zeros. And you would hope for 81 non-zeros, then they would all be 1. So these are roughly 120 non-zeros, but there's no clue in where to go for your split, maybe. Okay. I go now to the advantages or the good and bad things about mixed integer programming, and then we'll come to how we can use that for Sudoku. First of all, formulating it as a MIP, we can use the flexibility. First of all, we have one extra feature. We can choose our objective. The second nice thing that we immediately see here is that whether we were doing the standard Sudoku or the jigsaw Sudoku, actually the MIP formulation is exactly the same. Another thing within the mixed integer programming fashion is adding sets like on the main diagonal, we want to see every symbol once, or another sub area of 9 cells, whatever you like. They can easily be added. It doesn't change the structure. And so mixed integer programming is a very rich language to express combinatorial problems. Everything combinatorial can be turned into a MIP. On the other hand, methods to solve MIPs are readily available. They are generic. They don't need any domain knowledge. And they have already been developed since World War II. So in over time, the theory, the software, the hardware has already developed very much. And in the current times, we can really solve MIPS with up to 1 million variables and 100,000 constraints easily. Or at least, well, easily. We can easily set them up, and a lot of them can be solved easily. And I have to say, I will come to that later, that the success or the speed for finding a solution does depend on this LP relaxation. We will see that combinatorial optimization problems can sometimes have different ways to be formulated. They are all equivalent in terms of, say, 0-1 solutions, but they may have different linear programming relaxations, and by that, different success rates on the branch and bound process. So, but usually it can work. It may work. Sometimes it may not work, but that's inherent. If a MIP is so rich that you can formulate every combinatorial problem as such, you cannot hope that you always find a solution rather quickly. But for the Sudoku, it is really not a problem. We will see that this branch and bound tree will hardly need more than 80 nodes or something. That's just peanuts, really peanuts in our field. Yeah.
Sorry, Cor. Somebody else started to. Can you share your screen again?
And I have to go back to. Yeah, I have to go back to. Oh, hervatten even. Yes. Yeah.
Yes, it's working.
It's working. Yeah. Now I have it. Where do I have it? Yeah. Now you want.
Yep. Full screen.
Full screen. Okay. Yeah. So back at designing Sudokus. Now we really get the hang of it. The whole idea of this using mixed integer programming.
Sorry, Cor.
Yeah.
The question is, what was gamma again? Somebody asked.
Okay, gamma is the cost coefficient in the objective. So here in the MIP formulation, we have a variable. It has to obey certain restrictions. But in optimizing, we always look for, it's the cost coefficient here. Every X has its own private gamma, which we will select the way we need it. We will see how it works out. So, okay, if we come to designing Sudokus, okay, we have our matrix scheme. We know the number of rows and columns. We have a block structure. We may have some preferences of filling in numbers, but usually we start, say, with an empty table. And now we're asked to produce a completed Sudoku table together with a minimal set of clues in such a way that the current solution is also really the unique solution given the clues. And I will show how we can use the MIP facilities to build and modify our Sudoku. We will play with the objective to create an arbitrary objective solution. We can also use the objective to find alternative solutions. If the set of fixtures is leaving room for alternative solutions, of course, then we will play with that parameter to have fewer and fewer alternatives until we have only one, the unique solution. And then we have to take care, because on the way of extending the fixtures, we may actually include too many of them. And then we want to get rid of a few of them. So here are the things that you do with designing a Sudoku. First, to find the target solution, a simple procedure. I mean, you can do it many ways. One simple procedure is pick an arbitrary value for every objective coefficient, take the optimal solution. And usually we start with an empty set of fixtures. Now this is maybe more interesting. If for a set of fixtures we have found a solution, we already know this the created solution, of course, is stored. The target solution x hat, that is supposed to be the only solution. Given a number of fixtures, if we want to figure out whether there would be an alternative, then the objective is used by setting it equal to the 0, 1 vector of the target solution. And then we solve a MIP, look at the solution value, which is effectively the inner product of the new solution with the target solution. And we better have 81 or n squared in general. If it's n squared, in my MIP, we went for a minimum. So if there exists an x that has some ones in another position, then this inner product can become lower than n squared. So then it would have found it. So, okay, if the value is n squared, then the MIP for that set of fixtures has a unique solution, namely the one that we started with. If it doesn't, then we simply focus on the cells where there is a difference. We pick one, say at random, fix the outcome of that symbol on that field by setting the parameter fix to 1, and then we come back, resolve the MIP, test whether it's unique. If it's unique, we stop. If it's not unique, we go again to this set of differences, and so on. And at some point, you get stuck. You have the only, you have a unique solution. But this set of fixtures may not be minimal, so then we have to redo the procedure in a backward fashion. So a set of fixtures is minimal if dropping any of these fixtures will give you an alternative solution. So they all need it. And how do we find it? We have our currently found set of fixtures. Usually my idea is pick a random ordering of these row cell symbol combinations. You go through the list, you loop through it, you test whether you can drop it. If you drop it, leave it dropped and go to the next. You go through the loop. In the end of the loop, you will have found
and I could go
set of fixtures.
I want it faster.
And
how do we find it?
We have our currently found set of fixtures without creating alternative solutions. So this is how we found it. Usually my idea is pick a random ordering of these you may have seen that row cell symbol combinations. There is some randomness. I did things you go through the list, you loop through it, order, you pick a you test whether you can drop it. If you drop it, leave it dropped and go to the next. Things in different orders, you go through the loop. In the end of the loop, you will have found so you may try a set of fixtures of which no get nicer results. Fixture can be dropped is not per se without creating alternative solutions. So this is how we found it. Of clues. That's not per se a difficult when you go through this process, you may have seen that. But of course, you don't want there is some randomness. I did things in a certain strictly necessary. So it's always good to get rid of these extra. In practice, for the standard Sudokus or for the jigsaw Sudokus, which is the same for me, an automated run through this procedure, I usually create 33, 34 fixes before it gets unique. And then I get rid of another 10 in the second round. This means that I have to solve this Sudoku 66 times, roughly, but it takes like 10 milliseconds per time. So all in all, you can do this on the fly. So you can build your tool if you really want to build them with some computer support and also with some manual action, you can say, okay, give me the size, 9 by 9 is not strict. Give me the block structure. Then start with an empty set of givens, set random cost, solve the model, store it, set the cost such that you find alternatives, solve it. As long as the solution value is lower than n squared, fix a random position, so it will randomly pick something that was not fixed yet, solve the model. Okay, you can do it by hand, of course. The easiest thing is to run a procedure that does everything for you. I want to close with focusing a bit on the variant that was also mentioned by Hans Santema, the Futoshiki variant. So you have a n by n square where you need to have every symbol in each row once, in each column once, and satisfying some comparing constraint. So you compare, for the picture here, it's easier to compare adjacent cells, but maybe you can color code it and make it a bit more difficult. So there are a number of restrictions on that a number should be. Here you can only have a 7 or a 6. And actually you can only have a 6 because here you need a 7 for this example. And again, also for this one, you can do the same. You can randomly generate a Sudoku with every symbol in every column once and every row once. Given that outcome, you can compute how neighboring cells compare in horizontal or in vertical way. Then you start with 0 fixtures. You compute an alternative solution. If there is an alternative one, you fix either a number or a comparison in horizontal or vertical way, recompute. You do this a number of times. Of course, you also do this in a automated way. And again, this is milliseconds. One special thing I want to mention, what I used Sudokus for in teaching optimization and mixed integer programming in particular, is to have a problem that all students know, for which it's kind of natural to find a formulation. Okay, that's a first step. And then once you have this step, that you can use it for the purpose, for instance, for finding these, to design Sudokus. And I use this to see, to make the students see how certain procedures for solving MIPS work. You can use different solvers, and the better the solver, the faster it will work. So this branch and bound process depends a lot on what machinery you use. But it also depends on the formulation. As I said, the same combinatorial optimization problem can have different formulations as a MIP, which have different outcomes as linear programming relaxations. And here's the example for the Futoshiki formulation. Of course, it has the same rows as the Sudoku. Every cell has to fill with a symbol. For every row symbol combination, you have to pick a column. For every column symbol combination, you have to pick a row. But then we don't have blocks. We have pairs of cells, RC, RC hat, for which you want to have the left one lower than the right one. So these are the fixtures. And one way to express it is to take this sum over the variables, and by multiplying the x variable with the coefficient s corresponding to the symbol. So yeah.
I'm sorry, Cor. Again, somebody interrupted, so we don't see your presentation.
It's my last one.
Yeah.
Has he been removed?
Yes.
Okay, so I have to It's still, oh, hervatten, yes. Oh, where is it?
Yeah, now we see it again.
Okay, so this is my last slide, but okay. What I want to stress here is that, okay, when teaching my students, I need to make clear to them that, okay, one thing is that you have different ways to express the same problem. In particular here, say, if you want to formulate that some neighboring cells, or it doesn't not need to be neighboring, but any pair of cells where you want to have a value to be strict less than somewhere else. This is a way to formulate in a compact way this summation over S times X over RCS summed over S amounts to finding the value that will be on position RC. And for this, to do it on that one, you will find the value in cell R hat C hat. And then we say the first one should be at least one less than the second one, right? That corresponds with what you want. So this is how you can express it. And here below, we see an alternative. You can also see for the same comparison, if we fix a symbol, then we can say, if you dare to put this symbol there, if you dare to make this variable x equal to 1, then there better be an S hat with a value higher than x than S put on position R hat C hat. Otherwise, you cannot satisfy it. So if this variable is 1, the sum has to be at least 1.
Yeah, it happened again, Cor, but I think you're at the end of the talk.
I'm at the end of my talk, so I can say, well, I used the notion of, I used Sudokus for the purpose of teaching mixed integer programming.
Yeah.
And as a side product, of course, I have now a tool with which I can solve Sudokus, which I actually never do.
Okay.
I still like to do them by hand.
Yeah. Is the tool available actually? I mean, if somebody wants to use it, or
the code is readily available. The only tricky part is if you want to have a good solver, like Gurobi or Cplex,
yeah,
you might need a license.
Oh, I see. Yes. Okay.
And if you go for a cheaper, free available MIP solver, then you can find problems.
Kai, can you please switch off your microphone?
Yeah. Some people forget to switch off the microphone. Yeah.
Cor, thank you very much for your nice presentation.
Thank you.
There's you also know the killer Sudokus that Hans, I think, introduced as well.
Yeah.
It would be possible to write to adapt the program to that as well, I presume.
Yes. So I showed you how you can formulate the outcome of a cell. I say sum of weighted x variables.
Yeah. Oh, yes.
So and then you take the summation over those things in the area for which the sum was made, and then you can do it.
Yes. Okay. It's quite a bit of programming probably, but yeah.
No. That would be very easy. So I think the link version of Hans would involve a little bit more if you want to have also the connectivity of the network that you want. Yeah. But it's also doable because that's also in mathematical language or in MIP language reasonably easy to express.
Yeah.
Which ones are adjacent, and then you need to add some additional variables to be sure that you can reach everything from one cell.
Yeah. Are there any questions from the people in the audience, by any chance?
Yes, I would like to ask if you have, if you want to design a normal Sudoku, but with a particular pattern. Is it possible with your approach?
Yes, you can, of course, favor using the objective. First say, okay, this type in the pattern I would like. So, okay, leaving out things in the fixing part, you can also have some influence on the pattern. But if you want to have certain symbols somewhere, you start by fitting the objective instead of taking everything random. you can already start with, say, okay, these are my preferred allocations. And then you can still have the rest random.
Preferred if I say I want exactly these locations given and the other locations non-given.
Then you fix them
And
a priori.
with exactly this pattern, a Sudoku of a particular hardness. Is that possible?
I think you would only do it in the way you do it, say, okay, well, when you produce the fixtures and when you decrease the fixtures, then you can focus on your pattern. So I was more talking about if you want to have 1, 2, 3, 4 in the corners, okay, put them there.
Yeah.
Yeah. So the thing is, this is very flexible, the whole thing. So as I said, I even think I can do your linked version.
Okay, well, let's discuss this offline.
Yes,
Yeah.
yeah, we can easily do that.
Thank you.
Okay, thank you very much, Cora. In view of time, we have to go to the next speaker, but thank you again for your very nice talk.
Okay, thank you.
And then it's my pleasure to introduce Veit Elser. He's a professor at the Department of Physics at Cornell University. He obtained his bachelor from Caltech and his PhD from Berkeley. He then worked at AT&T Bell Labs, and since 1988, if I'm not mistaken, is with Cornell. And his group develops algorithms for reconstructing particles from noisy diffraction patterns. And over the years, they have noticed that their algorithms perform very well also on some NP-hard problems. And these applications have become a second line of research. This is also one of the incentives for the talk today. And his talk is entitled How to Build a Sudoku Brain. So we're very curious, Veit, to hear what you have to say. You're still muted. We don't hear you, Veit. You're still muted. We see your presentation, but we don't hear you. I see the, yes, you can see the, please click on the symbol down there, the red symbol. Yes. Oh, now it's gone. It doesn't seem to.
It's
Can you speak a bit? Because sometimes I hear a sound. Does anybody know how we can resolve this problem? Oh, Veit, please get out of the system and come back again. That seems to be the advice.
Okay.
But now, but Veit, say something, because I think I heard you.
Can you hear
speak?
me?
Yes, we can hear you. Yes.
Well, it says
very
my
strange.
mic. It says my mic is turned off.
Yeah, no, but don't care. I mean, it's
All right.
working.
Okay. Strange. Okay.
Yeah, very strange. When you talk, it turns green. Maybe it's an automatic system.
Okay. Can you hear? Can you see the presentation?
Not yet, but yes, now we can.
How about that?
Yeah, very good.
All right. Let me go back. Okay. Sorry for the rough start. So
No problem.
yes, this is supposed to be a recipe for anybody who's interested in programming a Sudoku solver, but who wants to do it in the simplest possible way. I call it the Sudoku brain because it's built out of very, very simple operations. But let's first agree that if we want to call it a brain, it should have these design principles. It should be deterministic. We should not allow any guessing or randomness. Also, we would be very sad if it had to track down many, many possibilities. That is also not what we associate with a brain. So as I'm describing this very simple Sudoku solver, you can ask yourself, how is it possible that doing something that simple is able to mimic logic? So this Sudoku brain has two kinds of neurons. So you think of a neuron as like the transistor of your brain. It's carrying out the most basic operation. And we'll first describe what I call selector neurons, and then later we will need also equalizer neurons. Okay, let me try something here.
Bandir, can you please switch off your microphone?
Okay, can you still see the presentation? Hello?
Yes, we can, yes.
Okay.
Yes, you can. We can.
Okay. The selector neuron receives 9 inputs and it generates 9 outputs. Okay? You can guess why the number is 9. And in fact, the rule is extremely simple. You see in the output at the bottom, only a single cell can have the value 1. All the rest must be 0. And I think if you look up at the input, you can see the rule. The rule is you just find which cell has the largest number. In this case, 1.2. That's the one that is the cell with 1 in the output. Okay. Okay, so that's what I was just talking about. Now, the position of the 1 is what matters, and it's selecting 1 of 9, and this comes up in 4 different ways when solving a Sudoku. The first way is you have to, for each digit, like 5, and each row, like the 4th row, you have to decide where, in which column, this 5 will be. So you have 9 choices of column. And similarly, you have 9 choices of row for each column and each digit. You also have, within each of these blocks, a choice of where to put the 4. So again, for all of the things I've described up to now, there are 9 times 9 such choices that need to be made. And finally, let's not forget this one. If you look at every single cell of the Sudoku grid, you have to decide which digit to put there, okay? So again, you have 9 choices, and there are 9 times 9 as many places where that choice needs to be made, one for each row and column. So those are pretty simple. Now, let's talk about the state of the Sudoku brain. Those were just the basic operations. The state is described by numbers, and these numbers are arranged in what I'm going to call a Sudoku cube, which is 9 by 9 by 9, okay? And in this cube, we have 3 kinds of columns. I'll call the ones you look at when you see a puzzle, the ones in the plane of the newspaper, as horizontal and vertical columns. But there's another column which I will call azimuthal, and it points out of the plane of the puzzle. Here's a picture, okay? So, you know, here's this cube, and there's all these numbers in the cells of this cube, and the interpretation of these numbers is the following. In a solution, okay, you should only have zeros and ones in this cube. And in particular, if there is a 1 in that position marked with the arrow, it's telling you that you have a certain digit at a certain position in the plane. Here it is shown in a different way, right? So if I have a 6, digit 6 in row 5 and column 4, there would be a 1 in that red cube shown on the left. Okay. So how do we arrive at a state of the Sudoku brain where we have these ones and the rest 0 arranged in the proper way? Well, the idea is to use selector neurons. So suppose we did the following. We apply selector neurons on all the azimuthal columns, right? Those are the ones pointing away from the puzzle. So after we apply the selector neurons, we will know that there's exactly a single 1 above every grid on the Sudoku puzzle, which is selecting the digit, okay? That's good. On the other hand, you now don't know if maybe you picked the same digit on one row or a column, which is just not allowed in Sudoku. But we can take care of that by thinking about another Sudoku cube, okay? We have a different Sudoku cube which is concerned with this other constraint. Namely, that on all the horizontal columns, we have just a single 1 and the rest 0. Okay? Of course, you know, for this Sudoku cube, certain other constraints will not be satisfied. But I want to emphasize the fact that the operations on these Sudoku cubes are extremely simple. The computation happens on just 9 numbers at a time, and they happen in parallel, independently on all 9 times 9 columns of the 3 types, and also the blocks, okay? So let's see. I've shown you 2 cases, 2 constraints, the digit constraint, which is azimuthal columns, the row constraint, okay, which is the row column, and then you have, well, okay, I'm saying now by using your human brain, you see how this is going to go. We will use 4 Sudoku cubes, okay, and apply selector neurons on them in the different ways for the different 4 different kinds of constraint, but now we have to we have to confront the problem that these 4 cubes will have different values. And what we really want is a single Sudoku cube that satisfies all 4 constraints. So how is that accomplished? Well, the trick is to use equalizer neurons. Okay, so here is a little notation just to make things a little more streamlined. I'm going to use the symbol X for a Sudoku cube. So that's an array of 9 times 9 times 9 numbers. And I have 4 of these Sudoku cubes. The X1 cube is going to take care of my azimuthal columns, the choice of digit. And I'm going to use the notation where P, capital P1, acting on the Sudoku cube, it represents that operation of applying the neurons. Okay, and so the combined operation of all 4 sets of selector neurons on the 4 Sudoku cubes is shown in that lower line. Okay, just you do each set of neurons is applied to its cube. All right, let's get to the equalizer neuron. Remember, we have 4 cubes, and so those should agree at every single element at each of their elements. And so there are going to be 4 values. Now, suppose the 4 Sudoku cubes at some point at some element have different values, like 0, 0, 0, and one of them is 1. So they're not equal. The equalizer neuron does something extremely simple. It just returns an output where all those numbers are equal. In this case, I have set them all equal to 1/4. Now, you would ask, like, why did I choose that equal value to be the mean or the average of those inputs, right? The average of 0, 0, 0, 1, 0 is 1/4. And the answer is that choice minimizes distance. Okay, so here it is in math. If I have a vector of 4 numbers, an A1, A2, etc., and then I have another vector where all the elements are equal, okay? And I'm interested in minimizing the distance between one and the other, okay? Simple math exercise, the A overline, which does that job, is the mean. Okay. So let's get back to Sudoku. And remember, there are clues. We have to input the puzzle, namely what digits go, certain digits have to go certain places. Well, it turns out at the stage where you're doing equalizing of the 4 cubes, that is the natural place to impose these clues. And so what we're going to do, I'm going to define this function C, okay, that does the following at each point I, J, K in the Sudoku cube, all right? So so when I say I, J, K is a clue, it means we know there is a digit K at the position I, J. That's one of those clues. So if we have a clue at I, J, K, then it doesn't matter what the equalizer neurons are saying. We know there should be a 1, right? We know the fact that there is a digit K at IJ. So we put a 1 there. But if we have no clue, we just leave it alone. Okay, so that operation C is very simple. Okay, so here's how we would now write the action of the equalizer neurons using math notation. Okay, input is 4 arbitrary Sudoku cubes. The output, represented by equal Sudoku cubes, where the equal values are generated by equalizer neurons with the modification that if we already know the value that they should be equal to by a clue, then we just replace it by a 1. Okay. Finally, yet more, let's make the notation even more compact. So if you think of those 4 cubes of 9 by 9 by 9 numbers, you can think of the whole thing as being just one array of dimension 4 times, okay? So let's call that y. And then I have just these 2 very basic operations that are going on in my Sudoku brain. One is when I'm doing selecting, that's denoted by PS. And then I have this equalizing operation, which I call PE. All right, so those will be how I express the workings of the Sudoku brain. And now, finally, we're getting to the stage where how does this thing work? Okay, and it's a dynamical system. It starts somewhere and it ends up somewhere, and the place it ends up should be a solution. So that the trick is to come up with a way of combining these simple operations, PS and PE, so that the state of the Sudoku brain that's generated, Y0, Y1, the sequence of states eventually ends up as a fixed point. So it stops changing, Y star, Y star, Y star. And that this Y star manages to be a solution. We'll get to that. And we also want this to work no matter where we start, no matter what we pick for Y0. Okay. So here it is. Here's the magic formula for a dynamical system that achieves these goals, okay? And notice the formula is expressed as, you take some input array, Y, of numbers, and then you get an output array, Y prime, and it's computed using very simple things, okay? There's these equalizer neurons that are acting sometimes, and then you can see there's a place where you double the values, that's the 2, and then you subtract, and then you take the result of that, and then you apply all these selector neurons, etc. So one application of this rule we'll call a cycle of the Sudoku brain.
It's fine. Can you remind us what RRR stands for?
Oh, yeah. It has a long story. Maybe we should wait until the
okay,
end.
Good.
Okay. For now, let's just say we tried a lot of ways of combining these operations that are obviously useful, but this one really works, and let's see if we can understand why. Okay. And so if we do have a fixed point, okay, so Y and Y prime are equal, and we'll call the equal value Y star. If you look at the upper equation and you set Y equal to Y prime, you can see that one of those, the output of the PS has to exactly match the output of the PE, right? Because if they don't cancel, then Y and Y prime will be different. So the only way to make them match to get a fixed point is they have to be equal. Okay, so the equation at the bottom is the condition for fixed points. Now let's study that. And this, the beauty is there's not much analysis. If you say those two are equal, we actually instantly know it's a solution. Well, Z is a solution. Why? I'm not saying Y star is the solution. I'm saying Z, the equal value. And why is that true? Well, think about it. Z is, first of all, the output of of all these selector neurons, right? So all the 4 Sudoku cubes are correct. They all satisfy their respective constraint. But we also know that Z is the output of the other operation, equalizer neurons. So because of that, we know all four Sudoku cubes in Z are the same. So there you have it. All four constraints are satisfied in a single Sudoku cube called Z. Okay, so let's have fun and see how this works. I went to a YouTube site which showed a video of the exciting final round of a contest at your university. And as you can see, the YouTube, I've captured a frame near the end where they're solving things in, I think, the final round of the competition. And I just copied that puzzle over on the right. Okay, so we're going to we're going to give our Sudoku brain the same challenge given to these very, very talented competitors. So here it is. Okay, and if you want to follow this yourself, if you're curious, if you can tell whether there's some kind of reasoning going on, perhaps, the animation is at this YouTube location at the bottom. Okay. So I've slowed this down enormously, of course, so it renders 1 cycle per second. And you might wonder, like, why are some of the digits? Well, first of all, you might wonder, what is this even a picture of? Okay, so the answer to that is that a Sudoku cube has just too many numbers in it to be able to interpret. Okay, so what you're seeing is when you look on these azimuthal columns, right? Those are the columns that are selecting the digit. Okay, and if you look at the Sudoku cube that's coming out of the equalizer, right? So at least all the Sudoku cubes are in agreement. Then those numbers on the column, on those azimuthal columns, will vary in value, right? If there's a large value, it's saying, I think the digit should be at that position. So you are seeing in this animation the current estimate of what is the most likely digit. And if it's rendered in a dark red, it means it's rather certain. And if it's a faint rendering, it means it's not the value in that maximum value was not very large. Okay, so I'll show you another example. Oh yeah, before we do that, you can make a compact representation of what was going on in terms of how much those values were changing from one cycle to the next. In other words, the distance between y and y prime. So that's plotted vertically versus cycles. And you can see first it goes down and it looks like it's going to be an easy puzzle because it's getting closer and closer to the fixed point where y and y prime are equal and distance is 0. But then you see it kind of goes up a little bit and then before it finally goes down. So this would be a typical kind of medium level Sudoku, would look like this. Now here's at some point this was claimed to be the most difficult Sudoku created by mathematician Incala. If you apply the Sudoku brain to this one, it has to do a number of, it has to restart in some, maybe it looks like 1, 2, 3, at least 4 times in a different way. So this is very much like this chaos phenomenon in Maria's talk. Yeah, so let's see what that looks like. Okay, again, this is available on YouTube if you want to follow it. Right. So as this is finishing, I think this is the end of my talk. I want to encourage anyone who is at all interested in programming Sudoku to try this out. I promise you, it'll be the simplest solver you have ever programmed. And not only that, it's quite fast. Now, we're just about at the end. I have given the PDF of this presentation to the organizers. And at the end of the presentation, which I'm not showing you, I have an appendix of extra information that you might find useful. So I think we're just about whoa, okay, it was close. It was very close. Okay, here goes. No. Okay.
I thought we were there, but no.
Yeah, right. Yeah. Okay. Hey, it's no joke that it's the hardest Sudoku. Okay.
No.
Okay. All right. As I said, so here's about 4 pages of additional information, but maybe it's a good time to take questions.
Yeah. Okay, fine. Thank you very, very much for this very nice talk. And indeed, if there are questions, please post them. I have one myself. I mean, so you define this operator that really makes the thing converge, yes, to the fixed point. So this PS of 2PE minus Y, etc. Have you tried any other ones? I mean, are there any other ones you think, or? I mean, it
Sure.
looks a bit like numerical.
Yeah. All right. So a bunch of this is in the appendix, but the short story is that there's a long history of using these types of algorithms. They're called projection-based algorithms.
Mm-hmm.
But all of that work has dealt with a class of problems which we would call easy because the constraints are convex. Okay, so there have been a lot of such algorithms proposed for that easy class of problem.
Mm-hmm.
Almost none of them work for Sudoku because the constraints are non-convex.
Yeah.
What's special about this one, which I call RRR, it used to have a different name, is it works really well for non-convex constraints.
Mm-hmm. Okay, there's another question, Veit. What is the walk time to solve the most difficult Sudoku with this algorithm?
What is the wall clock time? Is that what the question was? Hello? Hello? Uh-oh. Am I muted? What happened?
No, you're not. But I think Will just get frozen.
Yeah.
Oh, okay.
What is
So
most difficult?
I will assume
Yes.
the question was about wall clock time. Well, of course.
No,
yeah,
no, we hear you.
You can't hear me?
Yes.
You can't.
Yeah,
Okay.
we hear you.
Right. Okay. The wall clock time can be milliseconds if you write the program in C, and it can be even faster if you are able to use the parallel the property that the operations are so easy to parallelize.
Oh, okay. Can you hear me now?
I can hear you now. Yes.
Veit, or?
Yes. Hello.
Oh, okay, good. Yeah. Are there any other questions, maybe? So convergence is really, I mean, so the of hardness that can also be associated maybe with a number of steps that your algorithm is taking. Yes.
Exactly. Yes. And in fact, if I've made a careful study of those statistics on much bigger problems, you know, like if you want to study the complexity, you should be working with 100 by 100 Sudokus. Okay, so this algorithm scales really well. You can do 100 by 100, and in that case, it's closer to what physicists do, you know, like statistical analysis. And you can plot, you know, Maria was showing you this exponential behavior. You can get these nice exponential assessments of difficulty. Okay, so you have a steep slope when it's easy, you get a shallow slope when it's hard. It's the same thing. It's the same thing. It's I don't call it escape time. I call it solution time. I don't know. Average solution, or average solution time.
Yeah. Okay. Well, thanks very much. In view of time, we have to continue, but I think it was a very interesting talk, Veit. So thank you very much for contributing to this webinar. There seems to be a bit of a delay on the line, but okay. So thank you very much, Veit. And we go to the last talk of this webinar. And that is a talk by Professor Janusz. He's a professor emeritus of the Department of Mathematics at the University of Illinois. And he got his PhD from the University of Oregon in 1965. He retired already some time ago in May 2004. His main interests are in representation theory of finite groups, algebraic number theory, Brouwer groups, ring theory, and algebraic coding theory. But he also has an interest in Sudoku. I showed you already his book in my presentation, but now he will tell us about bugs in Sudoku solutions. So please, Jerry, go ahead. Just setting up the presentation.
Yes. So can you hear me?
We can hear you, yes.
I have my presentation on screen. Is that visible?
No, we don't see it. You have to share the presentation. Yes, now something is happening. Yes, now we see it. Very good.
Okay. So my presentation might be called the comic relief of this webinar.
Okay.
I'll begin by just defining what a bug is. A bug stands for bi-valued universal grave, or binary universal grave. The universal grave means that you throw out the puzzle. Since this is a mathematical seminar, I thought I should state a theorem. So here's the theorem. If the unfilled cells of a Sudoku puzzle each contain exactly 2 candidates, and if the puzzle has only one solution, then some row or column or block contains a candidate that appears only once in that row and is the solution for that cell. So I'll just quickly show you a almost bug puzzle. There's 18 unfilled cells, 17 of which have only 2 candidates. And a final cell has 3. So what I mean by candidates are the possible numbers that can be used to fill in the cell. So now I must prove the theorem that once you have this situation, you're essentially done. So it's assumed that every unfilled cell has one candidate that is part of the solution and another candidate that is the wrong candidate for that cell. So what do? You mentally fill all the cells with the wrong candidate. Don't write any of them down, but just imagine doing so. Now you have all the cells filled, but it cannot be a solution because by assumption, there is only one solution. So when you put in all the wrong candidates, you do not have a solution. So some row or column or block must be missing a digit. There's some row that doesn't contain all 9 digits or some column or some block. So let's say the missing number from a given row is D, and that D is not among the incorrect solutions. It doesn't appear because you filled all the incorrect solutions there. So D must appear among the correct solutions. And if it is part of a correct solution, it can appear only once. So when you have this bug configuration, all unfilled cells contain 2 candidates, and there are no hidden singles, then either there is no solution or there are multiple solutions. Here's the simplest case where there are 4 unfilled cells. Each cell contains 2 candidates. It's the same 2 in all 4. There are no hidden singles. No row or column contains a candidate only once. So the solution is not unique. If you enter a 5 here and a 6, and then a 5 and a 6, you have a perfectly good solution. But if you do it in the opposite order, enter a 6, 5, 6, 5, that is also a solution. Now here is a candidate, here is a puzzle that is almost a bug puzzle. All of these cells contain 2 candidates except one. This cell is the only one that contains more than 2 candidates. So your attention is fixed on it. And in effect, you can use trial and error to decide what goes here. But I'll point out that there's there's a clue for which one to select. First look at 6. 6 appears twice in its row. It appears twice in its column. And it appears twice in the block. And the same is true for 8. It appears twice in each row, column, and block. But 9 behaves differently. 9 appears 3 times in the row, 3 times in the column, and 3 times in the block. So that behaves differently than the 6 or 8. So you simply test it. If you enter a 9 here and then start filling in all the implications of it, so I would put a 6 over here. Down here is a 4, here is a 9, etc. You find the puzzle is solved. So 9 is the appropriate digit to go in E7. Now I want to approach the same puzzle in several different ways. This is exactly the same as the previous puzzle, except there's some colored cells. And those are there to help me remember how to solve some cells using not just trial and error on this cell, but to do it in a systematic way. I've taught a number of Sudoku classes, and of all the topics that I have presented, the alternating inference chain, I think, is the most subtle, and it's the one that is most difficult to find. So I will give an example of the chain of reasoning. So I start up here in A5. If that is a 2, then 2 is removed from C4 and F5. So if A5 is 2, then 2 is removed from the 2 blue cells. What happens if it is not a 2 at the start? What happens if we have 5 here? Well, then there are only 1 2 left. There were 2 2s in that row, and the gray cell is not 2, so A7 must be 2. And I want to ignore the fact that it must be 2 and concentrate on the fact that it is not 6. If this is not 6, then there's only one other choice for 6 in this column. So this would be a 6. But if that is a 6, it is not an 8. Not 8 means the other cell in that row must be an 8. And if that is an 8, excuse me, then it is not a 2. If it's not 2, the only other 2 in that row must be a 2. So the chain of implication was, if the gray cell is not 2, the yellow cell is a 2, and that removes the same 2 from the blue cells. I'll repeat that chain of reasoning with the same puzzle, but a different starting point. Let's start with with A7. If A7 has the value 6, then the 6 is removed from the 2 blue cells. So what happens if this is not a 6? Then it is a 2. So A5 is not 2. I'm I've been sitting here so long that I'm getting hoarse now that I started talking. Let me begin again. If this is 6, then the 6 goes out of the blue cells. If this is if this is a 2, then this is not a 2. Thank you. And so down here, this will be a 2. And therefore, this is not a 2. So this is 9. And that means this cell is not a 9. And therefore, it is a 6. And that removes the 6 from the 2 blue cells. So that's 2 examples of an alternating inference chain, AIC. I'll give one more, which has a different conclusion. Let's start with this cell, 2 or 5. If this if this is a 2, then the 2 is taken away from here, and this cell is a 4, and therefore this one is not a 4. And if this is not a 4, then a 4 must be present down here. If that is a 4, then it is not a 9. And there's only one other line in that column. So this is a 9. That takes away the 9 from here. So what has happened? If this cell is a 2, so is this cell. We get 2 2s in column 4. That's impossible. So our assumption that this was a 2 must be wrong. And this is a 5. If you start with the 5 and start filling everything in, you'll fill the whole puzzle. Let me give a simpler chain. This is a different puzzle. I focus on the green cell as a starting point, and the conclusion will be the blue cell at the bottom. So if A4 is 2, then H4 cannot be 2. So let's see what happens if H4 is not a 2. Then this is a 9. And so this must be a 2 because the 9 takes out the 9 from here. If this is a 2, then this is not a 2, so it is a 9. If this is a 9, this 9 goes out and this is a 2. And if this is a 2, this must be a 4. And if that is a 4, this must be a 2. So the chain starts with 9 here and ends with a 2 here. And so therefore the 2 can be removed from H4. A simpler chain of reasoning than previously, than the alternating inference chain, because we just move directly. If this was 2, this is not a 2, etc. In the Solving Sudoku book that I put together, I had searched the internet for what kind of techniques are most often used. And the technique I want to display here is called the X-wing for 2 rows and 2 columns. Let me go down and look at the puzzle with no colors in it, so that nothing special is highlighted. If you were trying to solve this by hand, as I regard as the only proper way to solve a puzzle is by hand, one thing you might begin with is just locating where specific numbers occur. And I would start with 1. So I look in column 1, there are 2 1s. This column has been filled. There are 2 1s in column 3, row B and E. All of the 1s are filled in here. Get over to here, there are 2 1s again. And in column 8, there are 2 1s. Now, if you have a good memory, you realize something is familiar about these 2 1s and the 2 1s over here. They occur in the same row. So I'll go back up and now and look at the colored cells. So we have a 1, a 1, a 1, and a 1. And it happens that the yellow cells are the only occurrence of a 1 in column 3, and also the only occurrence in column 8. So therefore, there will be a 1 either here and here, either B3 and E7, E8, I mean, or it will occur in E3 and B8. Well, that tells us something. Either E3 or E8 is a 1, and so this cell does not have a 1. The candidate cannot be correct. I call this the rectangle rule rather than the X-wing, because you can repeat this line of reasoning with three rows and 3 columns, or 4 rows and 4 columns, and they have names for those on the internet. The 3x3 is called a swordfish, and the 4x4 is called a jellyfish. Why swordfish and jellyfish should remind you of anything is completely beyond me. So I attempted to change the names by calling this case the rectangle rule 2x2, and the others are the rectangle rule 3x3 or 4x4. Although I have to admit, I've never seen a 4x4 in puzzles that I've come up against. I will do one last technique, and I don't have a new name for this, an XY wing, in which you look at three starting cells, D2, F1, and I2, if they were in a straight line, would be called a triple. 1, 4, 3, 1, 4, 3, and 1, 4, 3 are the three candidates for the three cells. When they're laid out in this configuration, they allow a conclusion. The gray cell is 1 or 3. We don't know which, at least not yet. So suppose it is a 1. Then down here, we must have a 4. Therefore, this cell cannot be a 4. If this is 1, then F2 is not a 4. We go the other way. If this is a 3, then this yellow cell is 4. And once again, this is not a 4. This is sort of a typical argument. These arguments work most easily when you have a lot of cells with only 2 candidates. So I think I've given examples of reasoning using cells that have only 2 candidates. The bug formation prompted me to look at these types of things. I'm trying to get back to the statement of the theorem. I see a typo. I gave a proof and a proof of something useful. So anyway, these are my examples of how bugs can be useful in solving a puzzle. The true bug configuration tells you when you can't solve the puzzle, but in the formulation here, if you have all candidates, all cells with 2 candidates, and if you know in advance that the puzzle has only one solution, then the puzzle will solve itself. You'll find a singleton someplace, and after you've plugged in that singleton and you clear out all the remaining singles, you'll still have 2 candidates in any unfilled cell. And so once again, there will be a single, and you finish the puzzle by just filling in all the singles. Okay, I think I will stop there because I can't talk very much more.
Okay, thank you very much, Jerry, for your presentation, and it's good to see how you solve Sudokus with by hand with these techniques. I mean, it's a good idea to rename maybe these exotic names like jellyfish, etc. Since indeed they are the same. I mean, they all use rectangles in the Sudoku. Do you think it's? I mean, so techniques like X-Y ring are they easy to use by human beings?
I'd say to experienced solvers who know what to look for, they do come up rather frequently.
Mm-hmm.
But for a beginner, it's a stretch. They may be hard to recognize. that's one part of Sudoku solving that I have never solved. How do you recognize the various techniques when you first enter all of the candidates into a puzzle? What do you look for? And that is an issue that's not easily solved.
No, that is true. I mean, I also I mean, X-wings are easily to detect, I think, easy to detect, but yeah, well, you have to check all the numbers, yeah? So, I mean, you did it with color, so that makes it a little bit more easy. You indicated all the cells where a 1 can occur, and then you observe the rectangle that leads to the X-wing, yeah? So,
That's
but
right.
you have to do it for all the numbers. Okay, are there any other questions for Jerry? So maybe a question to Veit. I mean, the technique that you were using for this setting up a Sudoku brain, would that lead to additional techniques for humans, say, to solve Sudokus, or?
Oh, absolutely not. Humans can't carry all those, so many numbers in their brains. Okay.
Mm-hmm.
I mostly try to make a parallel between the simplicity of the operation in the Sudoku brain and the simplicity of processing in human brains by neurons. And this is sort of more philosophical. You think we're capable of very complex logical reasoning, but the components of that are these neurons.
Yeah.
And so the broader question is, you know, how simple can you be in the processing and still have something which feels like logic?
Yeah.
Now, I'm not saying the Sudoku brain thing is anything close to the beautiful logic that we just heard with the bugs, you know, that it's not even close to that. But I think it's a nice challenge, especially, you know, now there's all this interest in neural networks, right?
Yeah.
Similar story. How simple can you make the processing and still have the outcome look intelligent, seem intelligent?
Yeah. Yeah. Yeah, I understand. Yes. Yeah. Okay. I don't see any more questions. So, Jerry, thanks very much for your explanation. I think it was very good. And I would like to thank all the speakers of today. It was a long session. I mean, normally at the conference we have a break, but we didn't plan a break. So everybody had to sit down and listen. But I think it was very worthwhile. I think we had a diverse set of speakers, and I enjoyed it a lot. I would like to thank all of you. I am wondering whether the director of the Office of International Affairs, Dennis, would like to say a few final words. Okay. 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 So we will all wait a few minutes. Indeed. Thank you very much. I think it's very kind of your university to host this webinar. I think it was a good experience. So, Veit, have you made any more difficult Sudokus in the meantime?
I've kind of, moved on to other things.
Yeah.
I don't want my department to think that I am only doing puzzles all the time. So I'm trying to make more serious. So I think what might be interesting for Sudoku people is who are also interested in neural networks, this algorithm, RRR,
Yes.
it turns out to be really, really powerful for training neural networks.
Oh, I see.
Okay, so this is different. I will still use the standard hardware of neural networks, right?
Yeah.
All of these activation functions, etc. But instead of training it by gradient descent, you can use constraint algorithms to train. And
Okay.
it turns out there are hard data sets that you can't train with gradient descent, which is the popular method.
Yes.
But it is possible to train with RRR.
Aha. Okay. So that's an alternative then.
It's just a fun application.
Okay.
Or a more serious application.
Yeah. By the way, you promised to say what RRR means. You promised to say what RRR means.
Oh, yes, right. It stands for relaxed, reflect, reflect. So the projection operation takes an arbitrary point and finds the nearest point on the constraint, right?
Okay.
And the reflection is you go to the nearest point and then you go beyond. It's like it's a reflection.
Yeah, yeah.
It's another geometrical operation.
Yeah.
So there are two constraints, right? We called one of them S and one E, you know, the selector and the. So it's like you reflect through E, reflect through S. That's the two R's.
Yeah.
And then the third R has to do with you make a combination of the result of the two reflections and the initial point. It's called a relaxation.
Okay. Yeah.
I told you it was technical.
Yes. Well, but it reminds me of numerical methods. I mean.
Yeah. No, relaxations are used all the time in numerical methods.
Yeah. So, yeah.
As long as there's a slight pause, I would like to express my thanks to Will for inviting me and for helping to organize.
It was my pleasure, Jerry. Thank you very much. So Denmark seems to be online.
Yes, sir. I'm here only. I'm hearing you only. Okay. So you just give the concluding remarks. Yeah. I wrote a mail to you also. Just say yeah.
So I already made some concluding remarks. So we were just waiting for the Vice Chancellor.
No, I think, sir, he is busy. So I wrote a mail to you. Yeah.
Oh, okay. So we can stop here. Okay, then I think I would like to thank again all the speakers, and I hope that everybody had fun in this seminar. I think we had some serious mathematics. We also had some fun mathematics, and maybe we can use the weekend to solve some Sudoku topics. So thank you again, and hope you're all well, and see you maybe in future time.
And thank you for organizing.
Okay.
Thank you.
Okay.
Thank you.
Thank you.
Bye-bye.
Thanks.
Thanks a lot, Phil.